use a clicker for this?
A clicker? What do you mean?
I don't know if it'll work on my computer.
Okay.
Just use the mouse, it's fine.
Believe it or not, we have yet one more thing of evaluations for you all to do. We'll get them out like before lunch or after lunch or something. This is evaluations specifically for the labs because the folks like the custodians and the maintenance people and the general office staff and the labs sort of environments need some kind of feedback from you on how things are going. It really shapes how we do things, so it's important to give us good feedback, not give us useful feedback, not trying to push you in a particular direction. All right.
We're not ready to go yet. We have like, I don't know, 7 or 8 minutes. But I think this is my last chance with all of you sitting in a classroom to tell you anything. And so I wanted to tell you a little bit about what this class has meant to me. So I started in this class in 1993. So this is 23 years or so of being embedded in a natural history-oriented biomechanics class at a marine lab where really cool gear is right next to the water and right next to the places you can catch the fish and the fish themselves. And I teach this class with my favorite colleagues every 2 summers. And it is, without even a close contest, the highlight of my life. This is, for me professionally, the absolute pinnacle of intellectual experience. I delight in getting pushed hard by all of you and the questions you ask that make me think about things that I would not normally think about things that I don't know the answers to. And so every time you ask me difficult questions, I have to go to literature, I have to start deriving equations on the board. This reminds me of why I love the job I do. And so it feels as though every time I teach this class, I look out at the students and I think, this is the best group of students I've ever seen in this class. And I wondered this morning as I got up and said, man, it's going to be hard to see this last set of presentations. And I realized I should say goodbye to this group of students in this place because they're the best students I've ever had. Could I say that? Could I really believe that after this many years of seeing the students? And the answer is absolutely yes. You folks made this summer for me a complete delight. The number of new things I learned was astonishing. And I think by now you know me, I really like to be on the steep part of the learning curve. And it's very hard to manage that all by yourself. In order to do that well, in order to do it effectively, it's best to gather to you the very smartest people, the very hardest working people, and ask them to kick your intellectual butt. And so you folks responded in spades. I mean, it was great fun. I appreciated every bit of good humor and hard work that you brought to this endeavor. And I'm really delighted in watching you support each other. And this class doesn't happen without an incredibly hard-working group of people. We had several teaching fellows in this course, led with unbelievable good humor and joy by Cassandra Donatelli, who brought so much to so many people's projects, and Dexter Summers, who was very excited anytime anybody offered him the opportunity to help. He said he wanted an app where people could put up a swipe left or swipe right for Dexter, come help me now. So I don't actually see him here, but we also had Colin, who is, I guess, late. And what? Was cleaning the tanks.
Yeah.
Yes! That is the kind of staff we have. Actually cleaning the tanks while things are going on. Donuts are being served and he's down there scrubbing out tanks. So Colin Dodger also put in quite a bit of work on the logistic end of things, moving things from one place to another. And I would embarrass her if I thanked her as thoroughly as she deserves, but Alice Gibb has been an absolute delight to be a co-instructor with. So she brought so much to this class that hasn't been in this class before. And so that's been a real pleasure. We are about ready to start, and these talks are great rehearsals for your presentation of these original materials at the Society for Integrated Comparative Biology, or if it's appropriate, some other scientific. But I really look forward to seeing how these projects develop and how they shape your career as scientists. So I think we should start right on time because people are tuning in from all over the world. How many users have we got now? Let's see. Let's see if we have anybody watching this. We have 10 viewers already. 10 viewers. I suspect that many of them are Fish class alumni who sat out there and they were wait, but he told us that was then. For the past. This is the future. You're going to see them one at a time. There, put it out on the web, ready for anyone. Okay, so I think we're about ready to start the first talk, which is by Noah Bressman, and I'll let him read his title and tell you all about it. Okay.
Good morning. So my project is on how intertidal sculpins aren't fat, they're just big bone. So for those of you who don't know what a sculpin is, these are sculpins. Sculpins come in a wide variety of shapes and sizes. This is only a handful of the hundreds of species of sculpins. You have some that are somewhat pelagic, like the silver-spotted sculpin. You have some that live in very shallow water, like the staghorn sculpin and the tadpole sculpin. You have some that live very deep down, like the northern sculpin and the longhorn sculpin. And you also have some that live in really shallow, extremely shallow in tide pools, like the tadpole sculpin. These sculpins that live in shallow waters and the tide pools have different challenges they have to face compared to the deep water sculpins. Specifically, the tadpole sculpins and intertidal sculpins have to deal with this. There are stronger waves constantly battering the rocks and the pools that they live in, and even the shallow species have to deal with stronger currents in the shallow water. To overcome these challenges, they need to still be able to hold their position. Sculpins are mostly benthic and they lie on their pectoral fins. If they're trying to maintain a spot on the ground while these waves are battering them, they need some kind of adaptation to help them hold on. Otherwise, they're going to get battered around and thrown throughout the waves. Also, intertidal sculpins can do this. They'll move around over land between tide pools, and they do this using what we call an army crawl. It's a combination of movements with their pectoral fins and their tail that allows them to move around over land. This puts extra strain on the pectoral since they're moving from a viscous force-dominated environment to a gravity-dominated environment. They have to be able to support their weight on land on the pectoral. So they may have a stronger pectoral girdle than the deep water sculpins that don't have to deal with these problems. So I wanted to see, do intertidal sculpins have denser bones? This could help them strengthen their bones and be able to withstand the waves and the extra forces associated with terrestrial openings. To do this, use CT scans of 35 species of sculpins from 24 genera, and I analyze them in Horos, which is a CT imaging software. I use the Grow ROI, which is a region of interest function, and I set it so it would select areas based on density, and I would select only bone down to the lowest density bone in the fish in order to exclude any soft tissues from the measurements. This function will give me an average value of density over the area in Hounsfield units. However, Hounsfield units have been proven unreliable as a unit of density for bones, as it can change from different scanner types and different machines. In order to solve this problem, I scanned 2 calibration phantoms. One is 25% hydroxyapatite, the other is 75% hydroxyapatite. Hydroxyapatite is the principal principal mineral in bone, which gives its hardness. And by scanning these 2 objects of known density, I was able to develop this function, where I would plug in for D the density of Hounsfield units, and I would get out the percent hydroxyapatite. I also did a habitat depth ranking using field guides and other natural history papers. I was able to determine depths at which these species are most likely to be found, and I've made a continuum ranking them based on this. So these are what pectoral fins of sculpins look like. These are the fin rays, and this is the pectoral girdle. A represents the typal sculpin, that lives in tide pools, and B represents the dusky sculpin, which is a very deep water sculpin. There are some very clear differences. Brighter colors reflect higher densities. So the typal sculpins have overall more dense bones than the dusky sculpin, which lives deep down. They have fewer pectoral rays, and the rays seem to be bigger and more robust. The overall pectoral girdle seems to extend more, and overall just looks like a stronger pectoral girdle than the dusky sculpin. To prove this, I found that the radials have higher ossification. This graph shows that the intertidal sculpins have a higher ossification than subtidal sculpins, as measured in percent hydroxyapatite. For those who know, the radials are the bones right here. Also found the same trend in the clithrum. The clithrum and the intertidal sculpins also had higher ossification than the subtidal sculpins. This is the clithrum right here. And I found the same trend for the fin rays. So the fin rays, they were denser for both intertidal and subtidal species. They were denser at the base of the pectoral fin rather than the tip of the pectoral fin. There are also, the intertidal sculpins had denser bones in their pectoral rays than the subtidal sculpins. At both 25% the maximum length, which is around here, and 75% the maximum length around here. So overall, the pectoral girdles of the intertidal and subtidal sculpins, the intertidal sculpins are more ossified than the subtidal sculpins. I also wanted to see if there was a linear fit for the sculpin pectoral ossification with depth. So using the depth rankings, where 0 has the lowest, the shallowest species, and all the way up to 33 is the deepest species, I found that the greater ossification as you go shallower, and ossification decreases as you go deeper. The same trend was visible with the clithrum. The deeper water species have less ossified pectoral girdles than the intertidal and shallow species. But it's possible this could have to do with the relationships these sculpins have. The intertidal sculpins and the shallow water sculpins is possible they're more closely related, which is why you're seeing this trend in bones, where you have all the related species up here and all of the other related species down here, and all the intertidal ones happen to have denser bones. We're using some comparisons like these, in which Clinicotis embryo and Orthinopius triasis are the most closely related species to each other. And Clinicotis lives shallower than the Orthinopius and has more dense bones. The Chitinotis pugicensis lives even deeper than both of those species, and it's fairly closely related to both of those species, showing that even among this group of sculpins, ossification decreases with depth. Isolinus peachy is another intertidal sculpin. Isolinus bertrami is a very deep water sculpin, and the same trend shows the intertidal sculpin is more ossified. Even among subtidal species, like Hemilepidotus spinosus and Hemilepidotus papilio, you can see that the shallower subtidal ones have a greater ossification than the deeper subtidal ones. I also noticed a trend in decreasing amount of fin rays as you move shallower. So the sculpins in the shallow water have fewer fin rays than sculpins in the deep water. So there could be some fusion of bones in the pectoral fin rays as the sculpins move into shallower waters, especially the intertidal subform. So again, these are fin rays, also known as lepidotrichia. And each lepidotrich, each fin ray, is composed of two halves called hemitrichia. So these are what a cross-section of hemitrichia will look like. To give you an idea, this is the vertebral column of a sculpin, this is the body, and this is a pectoral fin out to the side. You can see that there are two halves of the pectoral fin, of the hemitrichia. Each one is a hemitrich. And the one closer to the body seems to be larger than the one further away from the body. And the one closer to the body is also more dense. This right in the inside is where they are making contact with the substrate. Since they have their pectoral fins kind of against their body, by resting against the pectoral fins against the bottom, the inner hemitrich is the one that makes contact with the substrate. We found that this method is a viable method for a comparative quantitative analysis of bone density. And that each hemitrich, the hemitrichs that are located closer to the body and make more contact, greater contact with the substrate are more dense. This could be an adaptation to help strengthen the pectoral rays to make sure that they are better equipped to handle the increased interaction with the substrate than the distal pectoral rays. We also found that intertidal sculpins and shallow subtidal sculpins have greater ossification in the pectoral rays and fins than deeper sculpins, and the shallower sculpins also have fewer rays. This is likely to help them maintain their position better by having a more firmer pectoral girdle to grip onto the substrate with. This can help them support their weight out of water on land. Millions of years ago, when the first amphibious fishes like Tiktaalik went out, started making their way onto land, they also showed an increase in ossification of pectoral girdles and the fusion of bones, which is similar to what I've seen in these intertidal sculpins. I'd like to thank Cassandra Donatelli, Giordano Jimenez, Dr. Natalia Toft, Rajvi Bola, and the rest of the fish class for all their help and support. Thank you. Are there any questions?
I was wondering if you looked at any of the fin rays that aren't associated with the substrate to see whether strengthening is a general phenomenon of fin rays for the fish or whether it's just the pectoral.
It's the pectoral fins. I only looked at the pectoral fins, so I don't know.
What do you think, once you get out of the intertidal, totally in the subtidal, why would different subtidal species at different depths have the same kind of trend? You're living in water.
In shallow water, if you've been to a beach in shallow water, you see there's a lot more waves, and the waves get stronger as you get shallow. So a fish that lives in the shallow water, not necessarily in the intertidal, but still shallow, will have to deal with greater currents and a bigger, even wave force than the waves approach the shore. So by having a stronger pectoral girdle, they could more firmly anchor themselves to the substrate so that they don't get washed away.
For the species you look at, the individuals all kind of mature, so to speak, because that ossification can vary over time.
These are all museum specimens, so we used what we had, and there's a limit to the size of fish you could put into the CT scanners. They're all roughly the same size, but not necessarily they're the same stage of development. The smaller one, the smaller individuals for larger species, but I work with those available. Okay, thank you.
I think it would be possible, it'd be cool to like make a model, see exactly what forces are present, like, how much force is the pectoral? How much force are those?
Yeah, I'd like
To
to
see if those are the good ones to look at.
I like to see, like, compare the forces of forces that are supposed to tail for just locomotion. Make you see how the forces play depending on each of the different patterns.
So if you compare the like crash testing and the scientific testing, there, in testing they may have the house fire, guide, like reservation, formally, and all of these things. And how do you use
Now these making scans, do you know how much they were?
They were very low infections.
Okay. Thank you.
Okay, how do we get to presentation? Start from the first screen. It's a new announcement. Look at that. Ready? Hello, everybody. My name is Maddie Rich. And so I'm interested in how fish scale, how they change as they go from small to large. Because as I'm going to talk about a little bit later on in the lecture, if you look at something that grows on land, it lives in the same environment all the time. In the water, that's not the case. And I'm curious about how fish handle this fundamental problem of growing up in the ecosystem. So first, how do fish grow? What exactly is scaling? The first kind of scaling is isometric. Basically, iso, same. It's like if you take a cube that's this big and a cube that's this big. You wouldn't be able to tell what is what. Proportions, the geometric proportions are constant. In fact, as it grows. But if you look at allometric scaling, which is what you normally see in nature, right? Like if you imagine a baby that's this big with its head here, or even worse, a baby that's like man proportions, that would not be so good. So obviously this happens a lot in nature, and I'm curious, does this happen to fish as they grow? They cover a huge size range. You know, larval fish are this big, and the mola is 10 feet long. So how do different fish scale? And then how does that affect the motion? When I'm looking at elongate fish, I'm looking at certain methods, certain modes of how they move, such as frequency and stride length and velocity. And then what's even cooler is how can I explain what I see? How can I take these principles from these little fish moving around in the water to something that then can be applied to robotics, or how humans move around the water? We don't use undulatory movement in the water, we use propellers. But what if we're doing it wrong? What if there's something we can learn from these guys? So the fish that I chose, Penpoint gunnel, it's an intertidal fish. It lives in a really complex environment, so it's undulating a lot. And these guys are great to study because they cover a wide size range. And here I have a lateral view and a dorsal view of a large fish, and a lateral and dorsal view of a small fish. So about 4-fold increase. And you can clearly see the subtle differences. Oh wait, I mixed it up. That's the large fish and that's the small fish. And in fact, they are exactly the same. They scale quite isometrically. Here we have a relative height profile, relative width profile. The small fish looks the same as a large fish. What does that say about how they're moving in the water? What does that say about the kinematics? So when we're looking at kinematics, we have to quantify elements of their movement. And here I have a little example of the head being traced as the fish is moving that way versus the tail being traced. And so the elements that I looked at are things like wavelength, which is the distance of one full cycle. Amplitude, which is how high the tail moves. And from this kind of data, you can also get frequency, which is how many beats per second the fish's tail will make. Stride length, which is like I'm moving one full stride. And velocity, which is this total forward speed. So here's an example of a small fish swimming. And here's an example of a larger fish swimming. This is what I did. I then took these videos and ran them through a MATLAB code, which would go down the line of the fish, frame by frame for every single frame, and give me beautiful graphics showing the midlines of the fish as they move. So imagine this is the tail, and this is the head for frame 1, and the head, the tail for frame 2, etc., going down the line. And it also gives me a ton of raw data that I can play around with. And they're just gorgeous. So if you look up top, here we have a large fish moving, a medium fish moving, and a small fish moving. And this is all around the same distance. And immediately, things pop out to you, right? Like that large fish, there may be 3 beats, and that medium fish that's about twice that, and the small fish is about twice that. The large fish is moving its tail about the height of the small fish. So, I mean, there must be something different that's going on in how these fish can physically move through the water. Here, I've also traced out the path that the head takes versus the path that the tail takes. And what immediately jumps out at me is, well, A, the head moves much less. But B, the head moves about the same relative to the tail, no matter the size. So it's not like the small guys are really chugging their head along to make them move. You're kind of doing the same thing with the big guys. To get a little more quantified, here we have 3 wavelengths for that mass, 7 wavelengths, 13 wavelengths, and I plotted them and found that this relationship. As your mass increases, your frequency goes down by an exponent of 0.17. So how can I kind of put this into a context of how animals move in general? Well, a lot has been done on terrestrial locomotion. And this is a null model of terrestrial movement where you have the frequency of steps decreasing as you get bigger and your stride length increases. And because those two change slope proportionately, your velocity stays the same. So if I'm an animal that does this, so my frequency is very high and my stride length is very low, then I move about the same speed as an animal who does this. So these were developed for terrestrial models. And what I found in the water is something that's kind of similar. I mean, what's really interesting is that stride length, which is inherently, stride length, I'm stepping with legs. That's the same as stride length, like I'm moving like a ribbon through the water. What? Why would you expect that to be the same? So I'm wondering now, what other kinds of principles can be translated from land into the water, and what principles are different? So another thing that I looked at that I thought might be interesting is Reynolds number, which is basically, if you're in a high Reynolds number, about 1,000, you're in a world that's dominated by inertia. This is where whales, large fish, or we swim and move in the water. So imagine I'm swimming and I stop, but I keep going. In a low Reynolds number world, where your Reynolds number is much less than 1, it's like you're moving in molasses. So if I were to get into a pool of molasses, I would go like this. And I would try to reset, and I would go like that. And I would just be stuck in the same place. There is no inertia in this world. And a lot of organisms live there. For example, ciliates, and sperm cells, and most of the fish. So although a fish that will eventually end up in the inertial dominant world start off in this little viscosity. In between, we have no idea what really goes on. Mathematically, it's a black hole. We can't predict the forces that are acting on these creatures. And that's anything from like this big to that big, which that's a pretty small size range, but a lot lives in there. Most yellow fish live in that range. Reef fish, shrimp, other kind of plankton swimming in the water column. So keeping this in mind, I was wondering what happens to my fish. I didn't have their larval stages, but I had fairly small fish. And one thing that's interesting, velocity is a big factor in what Reynolds regime you're in. If you're going at a very low velocity, you're likely to be lower down in that graph. Whereas if you're at a higher velocity, you're going to be higher up. So if you look at their tails, they're moving through a lot more water. They're moving at a higher velocity than their heads. So, here I have plotted the heads of the small fish for an estimated Reynolds number. And if you notice, all of my small fish are in that we don't know what's going on for it. Once you get to the medium fish and the large fish, then they're pretty solidly in the inertial dominant regime. So that's kind of cool. Small fish are living in this weird place. And if these are the head plots, then these are the tail plots. it's expected that obviously the tails of the larger fish are still in that inertial dominated regime. But the head plots, the tail plots for the small ones are also kind of in this weird place. So does this mean that it's like I'm swimming with my head in molasses, but my tail is slipping in the water? Or does it mean that like sometimes half of my body feels like it's in molasses and half of my body is in water? So what on earth kind of world are these fish even experiencing? We have no idea. What's really interesting is that their movements scale so nicely and their morphology scales so nicely with their size. So it must not be that big, right? Like there must be some way that these guys are unlocking a way to move efficiently in this crazy world. So that's, I have to leave you guys, sorry. But what did we learn? We learned that eat-like fishes scale almost perfectly isometrically, even though they live in these different environments. Patterns observed in elongate swimming kinematics may be surprisingly analogous to terrestrial motion, and there's a lot that we can learn and do to try to unlock further similarities and differences. And Reynolds numbers might not have as much of an influence on you guys as expected. And I'm telling you guys, as soon as this comes out, I'm waiting for a call from NASA, like, hey, we need you to help figure out how we're going to move in Titan's methane oceans. Because who knows if elongate kinematics, so the way to do it. Or, National Institutes of Health, we want to move through human blood cells. And that's a pretty low Reynolds number environment. What if we need little beetles swimming around in us doing surgery? Like, that would be so cool. So, I'll wait for that. Acknowledgements, thank you to Harvard Laboratories, professors Adam Summers, Alex Gibbs, Cassandra gave me all the code that I used. Impossible without here. Welcome to Cotsy, helped me very much understanding scaling, and the rest of you guys would be awesome too. Did I have any questions?
I have more of a comment, just that, and I guess I could like do that with Adam and Sandra too, but I'm not sure I buy that the characteristic link of the fish isn't just the whole fish, right? So I'm not sure I buy the different Reynolds number for the head versus the tail. I think if you use the characteristic link, whole fish, you'll find that they're all mutually so that would be, yes.
I'm sure that would be something that would come out. But the main issue that I had with that is the different relative velocities for different parts of the body. But I also don't know, like, what is the fluid flow around it? Because in the head, you can assume that they move it further longer, but at the tail, they're probably not.
I mean, we've had a number of, swimming speeds for like actual really small fish, fish that are below a centimeter in size, and we've never seen. I would always expect if you saw a large Reynolds number influence that you might see some sort of discontinuous pattern as you move from one regime to another regime. And we've never seen a discontinuous pattern except for one that used to be more associated with formation of the tail swimming. So any discontinuous pattern we've seen seems to be better explained by morphology than by Reynolds numbers. If you pick up fish of a different size, it still is the tail fin that seems to change, not the size.
Right. So that could be broken enough to conclude about treatment.
It's possible. I just, as I said, I have a slightly different perspective.
Yeah, but also, how are those little fish moving? Are they using elongate swimming?
It's possible.
I have no idea, but maybe that's a way to kind of minimize the effects of
I started doing some calculations of trying to get things related to resonant frequencies, and you decide that there was nothing interesting there, or that it was too complicated.
Yeah, so apparently, what I was trying to do is see every, like steel rod, for example, a tuning fork, will have a frequency, you hit it, and it resonates at that frequency. There's the theory that if you're a fish, it's most efficient to swim at your resonant frequency, so that you're using the least amount of energy. But that doesn't really exist underwater, apparently, because A, you're a softer body than something like a steel rod is, and B, you have to deal with other dynamics of the water as you're going through it. So, talking with Cassandra, she said that people don't know about it, so it's foolish to try to solve it. I was wondering if anybody had any idea of where the these waves are starting? Are they truly the snout, or are they starting later back? And when we see a head nod, as we go with the tail, you know what I mean? Idea of what might be happening as they get started on the body.
I don't really know for sure. It seems like the waves really pick up. Let's see if I can go back to this guy. They really pick up like at about, this far down the body. But we also don't know if there's, is there something going where the head moving starts the propagation, or are they working on a whole bunch of muscles to do that? So I don't know how to look at that, maybe without seeing moves into the fish as they're swimming and seeing what muscles are activated.
But the second thing about what Alice was saying with the rigid, the mover rigid being kind of by the pectins, where it looks like it's originating, maybe that head down is just recoil from the tail.
Right, that's interesting.
Gary Gill's fieldwork has a lot of good EMG on, and actually he showed, and I think I was talking to Sandra about this, but I still don't fully understand the mechanics of it, but he showed that there's a lot more activation interiorly before the wave begins to be generated.
Yeah,
So that's kind of useful just in thinking about how it works.
We don't have time for another question.
They're getting more and more popular. We've already got 40% more viewers. We're up to 60. I got a note from someone saying they're doing job search lurking, so.
Not that there's any pressure. Yeah.
Okay, wait, hold on. That's the one.
Yes.
There we go. All right. So today I'm going to talk to you about the effects that lack of sleep and stress have on the Another talk for another day. All right. We are going to be looking at the contribution of the sternohyoideus muscle to powering suction feeding, specifically in striped perch. They're a surf perch by the name of Amblyotoca lateralis, and it wasn't on our test, so any of you might have forgotten it by now. So in a recent study, there was evidence that showed that in largemouth bass, the suction power that was necessary for suction feeding was actually coming from the axial muscles rather than the cranial muscles. If you think about suction feeding, it's all up the mouth, so you're probably going to assume automatically off the bat the muscles in the head, the cranium, are going to be what you need for that suction feeding event. Now, the Brainerd lab actually showed that if you look at the axial muscles and the cranial muscles next to each other, you're going to see that the power that the cranial muscles are capable of producing versus the axial muscles are going to be night and day. So we have some cranial muscles here that are listed, and that's going to be everything from the right of the hypaxials. And compare next to that black graph there that shows what's necessary for the suction event, you're going to see that the powers that the axial muscles, epaxial and hypaxial, are capable of producing far outweigh the cranial muscles. Now, just how you get these numbers, if you look at the blue bar, you're going to see these are the optimal powers that they are capable of putting out based on the mass of the muscle multiplied by that 216 number you see on the right-hand side there, which is a calculated mass for what the white muscle is capable of producing in fishes. So you have your blue bar there, which is showing the optimal, and then for any kind of power, you're going to need to make sure that the velocity that's putting out and the force that it's putting out are at the right kind of level where the velocity is going to be a 1/3 Vmax, which I'll talk about a little bit later. But if you see what the stripes of these bats are actually doing from that study, you'll see that for the median, they're going to be putting up about 10 watts per power capacity and a negligible amount for the sternum radius, meaning that that power is definitely, most definitely coming from the axial muscles. Now, even if you have the correct power for the muscles, there's another question of whether or not the timing of that power is going to be correct. So the next thing that was from the study showed that if you're looking at the timing relative to peak gait for the power that's produced through these guys, you're going to see that the epaxial muscles, the hypaxial muscles, are shortening, meaning that if they're actively shortening, they're providing power for suction. At the time relative to peak gait, where the sternum radius, the cranial muscle that was doing anything as compared to the other muscles which were way too small to put up any kind of substantial power, is lengthening at that time. Wrap it up. The epaxials and hypaxials are shortening. They have enough power. They're going to be the main ones that are causing the suction event. The sternum radius is doing something else. Not going to get into that today. But that leads the question, is there another fish that is potentially able to use its cranial muscles to provide enough power for the suction event? These guys here, the Ambiotopus lateralis, or the striped surf perch, are going to be pretty well known as some powerful feeding fish. Some of you even know decapitated if they're hungry enough. That means they're literally boiling the water with how much pressure they're making. Power they're generating. So these guys here, they have these tiny little heads, so we're still not sure whether or not they're going to be creating the correct power, but let's take a crack at it just based on the size of muscle alone. The question is, where does the power come from for these guys? We took a three-pronged approach where we're going to start by looking at the size of the muscle, followed by whether or not it's shortening at the right time, and then finally looking to see if the velocity that's going to be putting out is going to be right near that P optimum that I showed you earlier with the blue bar. So let's go ahead and get into the size. If you look at our bass here, you're going to see this kind of small sternum radius relative to the rest of the axial muscles here. And like I said before, axial muscles putting out the power, small sternum radius not doing too much. Now for these guys, cute little fellas here, you're going to see that the sternum radius is right in this section right here, which doesn't look too big compared to the axial muscles, but as I go on, you'll see that it's much more as compared to the bass. So I actually dissected out, skinned these guys, and I showed you this muscle. So where the bass is about, let's say like right here, these guys are going to be this whole area right under that pectoral girdle and the pec fin. Based on percent of the mass of what these muscles are putting up compared to the bass, so the sternum radius within the bass is going to be about 1.8% of the muscle mass of everything that's contributing to the suction event, whereas the Ambiotopus lateralis is going to have an average of 10 based on the muscle mass for, I think we had about 4 or 5 individuals. So that answers the question. It's obviously big enough. Let's see what's next. Is the sternum radius shortening at the correct time? We took the same approach as the Brainerd study, and you see here, we're going to be checking to see, oh wow, that's dark. You're just going to have to believe me that this is a dot, and we're using a technique called VROM. Oh, thank you, Evan. Let's see what we get. A little bit better. So we put markers on our fish here to track to see whether or not they are going to be shortening at the correct length without having to do the technique of fluoromicrometry. My video is not going to be working, I'm just going to keep moving on. But you're going to have dots here, one placed in urohyle, one placed in back of the sternum radius, in reference to a body frame. So we're going to see just what they're shortening during the feeding event, and it's going to give us, let's try it one more time. It's a pretty awesome video. Come on, guys. Ah, there it goes. All right, yeah. So you can see the beads are actually tracking with the muscle. Okay, it's sleeping. Yeah, the beads are tracking with the muscle, which is going to give us the shortening length that we need to determine if it's shortening at the right time relative to peak gait. So this is what you get after you do your animation for VROM, and you're going to see in the next slide that we can actually measure the distance between these points that are shortening and represent our sternum radius to show if, again, relative to peak gait, it is shortening at the right time. We throw the distance tool on there, and it is obvious based on numbers down there that we are getting the shortening that we need. And the next graph, you'll see just where it's shortening. So I kind of put a visual aid here because, you know, you want to break it down the best you can so people can understand, follow along with you. You don't want to make anybody do, just try hard. All right. Right here, this bar is peak gait, and relative to peak
PK, you can see the sternohydratus actively shortening. Epaxials actively shortening, hypaxials actively shortening, question mark? And the velocities are putting out will right along with that PK, giving the power necessary to be a part of the suction beating event, but we still can't say for certain whether or not they are going to be contributing without looking at the power they're putting out based on these velocities. So what then is the velocity correction power capacity of the sternohydratus, the epaxials, and the hypaxials, the surf perch, as relative to the largemouth bass? So kind of a quick little lesson here. If you look at Vmax versus the force max, Fmax curve here, so for your force, you're going to see that at Fmax, velocity equals 0, and Vmax, force equals 0. So right in the sweet spot here is going to be the optimal power that you're looking at for those blue bars that I showed you earlier, based on that 216 watts per kilogram. And I plotted that line for you here. So if we're getting these muscles to fire at the optimum power, they're going to have a certain velocity and a certain force that's going to be about 1/3 the velocity right here at the peak of that power. And again, visual aids, so you don't have to try hard. Okay, and for the means of the shortening velocities for all the different individuals you got, so you have 18 strikes with 4 different individuals at Minnesota, you're going to see that they're firing a little bit above Vmax for the shortening velocity, which is that 1/3 right here. That's the optimum that I talked about, as compared to the bass, which is laughably small for the shortening velocities. So again, strong power for their suction events, and they're performing just about where you expect them to be performing to get close to that 1/3 of Vmax for the optimal power. So they're not perfect, nothing ever is, but these guys are performing just within that range to say right where we need them to be. So the power capacities that we put out here are the averages. So these would be the equivalents of the blue bars that I showed you earlier for the ambient sodas and the bass. So the bass we changed to black just to kind of keep it the same thing. Averages or the optimal outputs for the ambient soda lateralis. So right here you're going to have about 14 or 13.9. Looks like 9 point something. But if you look, the optimal P-opt versus P velocity correcting, which is the red bar here, is going to be much higher for the ambient soda lateralis than it will be for the bass. They're all performing from sternohydratus all the way to epaxials. They're right there at the top of what they need to be, which again coincides with that graph I showed earlier, where they're almost on the tip of that power curve. So the next direction is then, because we know that they are capable of doing the velocity correction, we need to get the actual expansion power for suction events from these guys by checking what pressure is going on the mount to get the expansion power. Because as of right now, we can't give you an exact number for the expansion power, but we're going to base it off what we've seen for their performance near Vmax. I'm sorry, 1/3 Vmax for optimal power. These are the numbers that were put up by the bluegill sunfish. So you see right there, their expansion power is pretty high relative to the to the bass. And for our guys, we're expecting them somewhere up here, but as of right now, it's typical sciencey, hand wavy. You can't say anything for sure, but this is about what we're expecting. That's where we're going. Thank you for listening, and these are the people I'd like to thank. Different Friday Harbor Labs, everyone got me out here because I was broke. And of course, Thaddeus Buster and Sarah Hoffman. We are a part of the Vrom crew. It's, I think, Big Fatty Sculpin and the Vroms. Cassandra for all the late nights, everything you got. I'm sorry, Dallas, in the fish class. Thank you. Questions? What's up, JD?
Yeah, so early on, you were talking about like the first bullet point about muscle mass.
Yes.
You showed the graph, it was like percentage of the muscle mass, and I think you said like involved in suction feeding, so is that?
We were looking primarily at the epaxials, the hypaxials, and the sternohydratus, just because the first graph you saw with the bass, where all the other muscles that are involved in suction feeding and the cranial muscles were barely putting out anything, so we thought it was okay to just neglect them.
So the graph that showed the percentage, where it was like the
Yes.
that much higher, so that was percentage of those three muscles, like the axial muscles and the sternohydratus, what percent of those together?
Correct.
Okay.
Yeah.
So the theory is maximum power is that 1/3 maximum velocity.
130 max, yes.
So how many, is the range that you have for your fish typical for animals? Like, are most animals born dead on there, or
I actually don't know, but I'm just assuming that based on the fact that that's like the optimal, like right at the tip of the top, you're probably gonna see animals that lie somewhere to the left or right of that number. I can't think of anything on the top of my head that would be right on power, but I'm sure there's something in literature. As of right now, I'm assuming that they're just gonna be more suction specialists and there's gonna be other guys that are just kind of doing what they need to do to eat that would be farther off versus the suction specialists, which would probably be closer. Right on, I can't say for sure.
So, how much are you worried, so, I mean, muscle shortening was nothing with external markers.
Correct.
So, do you do like to see how you?
That's the next step. So,
Okay, so I'm just
yeah,
curious.
floor micrometry is used in wildlife studies right now, and that's where you're putting the beads right in the marker. We think that within 0.02% of VROM should be accurate, but we can't say for sure until we actually compare it against floor micrometry. So as of right now, we're assuming because we saw shorting, that'll be good, and we'll go from there because the projection areas that we're getting are pretty similar to that of XROM, actually, if you want to talk about this afterwards. But yeah, so can't say for sure, but we just think as of right now, good enough. Thank you. Do I have time or?
Yeah.
Yeah, sure.
if you could do the same thing for any other interesting.
I don't know, maybe someone confused John, just kind of see what they're putting out, what they have. I really need to have for that, such a thing. That's what I would say right off the top of my head. All right, thank you.
We're ready? So you're gonna introduce Sarah to start it off? Sure. Please tell people we're ready to go. 20 minutes. Oh, thanks. Hey, how are you?
Computer was purchased sometimes machine until I got my real computer, and then I never got a real computer.
No, it's not. It's not going to taste it. So it's got, yeah.
Actually kind of cool. The otoliths are super prominent on this. Yeah,
Oh, wow, look at that.
like, I thought it was an air bubble.
Yeah, yeah, yeah.
Crazy prominent.
It's just and it's not even red stained.
No, it's,
Wow.
I know. I was like,
Really
how did I get this
cool.
air bubble in there?
The surf perch?
Yeah, tell me if it's- like, yeah, you can see the fringe of it. Yeah, you can see the little ones on the other side. The other one I want you to so.
All right, guys, we're gonna get started again with our second round of fish class talks. And first up, we're gonna have Sarah Hoffman tell us about three-dimensional movement in terps. Yeah.
Perfect.
I see, okay. So, when I first came into grad school, I got really excited about pectoral fins and sharks because it reminded me of airplanes, and I spent my youth watching airplanes fly. I thought, here I can apply airplane mechanics to really cool organisms. And then I started watching sharks swim around and realized that they don't look like airplanes at all, and I'm not sure why in the early days they were modeled as these pectoral fins were modeled as fixed, rigid bodies that were hypothesized to produce lift, which is all of the early studies. And then some volitional kinematics came out, and it was hypothesized that pectoral fins might be adjusting trim, again, like an airplane, with the trailing edge of the airplane wing. And then Wilda and Lauder came along and found that the pectoral fins of benthic species of shark aren't producing any lift whatsoever. So this whole pectoral fins are airplane wings is out the window. And so that really led me to ask, what are these pectoral fins actually doing, and how are they moving in 3D space? And recently, a paper came out looking at pressure shark feeding kinematics and how they are using their tail to whip prey. And it turns out that they are actually abducting their pectoral fins like a brake.
First, it rotates its pectoral fins down to stop short.
This is about 3 seconds of like a 5-minute clip about how cool the tail is, but clearly the pectoral fins are the exciting part in this, little clip. And then if we look at a very specialized walking shark, like the epaulet shark, which will walk between tide pools, if you look at the pectoral fins, it just boggles my mind that anybody could think they are rigid objects. We see a huge amount of rotation about that pectoral girdle. So clearly, again, not airplane wings. And the way that this articulation is happening, I'll draw your attention to this rendering first. Here we have the joints, so the proximal body axis would be here, and here we have the leading edge of the pectoral fin, and these fibers that you're seeing are actually the collagen fibers that are separating the muscle in the protractor. And if you took a slice, a transverse slice through that, we're looking at the cartilaginous elements here. So here is the base of the scapula, and then we have the first basal element that is articulating with the scapula, and then the radial elements coming down the leading edge of the fin. So what we see is a pretty large articulation surface that would suggest a high degree of movement in this joint. So my question in this project was, what are the rotational kinematics of pectoral fins in sharks? And in order to do this, we anesthetized the shark and glued white beads along the rigid parts of the pectoral fin as well as the body axis. And then we woke the shark back up and let it swim around Shark Stadium, as you see here. And this is a setup that we are using for video reconstruction of moving morphology, or VROM. So what you see in these bricks here is a 3-foot by 3-foot by 3-foot grid that we calibrated between these two GoPros that are pointed at about a 45-degree angle to each other, so that we can use tracking in XMA Lab to produce these 3D coordinates. And from that, I can take those 3D coordinates, so I grouped them into 2 rigid bodies. The blue cylinder is the shark, and for the shark body, and the pink cylinder, or pink prism is the pectoral fin. If I play this, that is a lot of hours of really hard work. So this is the shark that's actually completing a turn. So this is a volitional swimming video in which the shark completed a turn in front of the cameras. And in order to look at the pectoral fin movement a little better, we froze the shark to the frame. And what you'll see here is just the prism moving in relation to the body. So to me, I see a huge amount of rotation occurring in that pectoral girdle. And in order to analyze this, we assigned these joint coordinate systems where we assumed the articulation would be, and then we chose the best coordinate system based on the amount of translation, or rapid translation, hopefully. And we can track that movement. So these arrows moving are showing you the rotation that's occurring along 3 axes of the body. And if we look first at that volitional swimming video, all of my graphs will be set up like this. So I have frames or time on the x-axis and rotation in degrees along the y. And we zeroed the joint coordinate system at the frame previous to the behavior. So 0 is at 10 frames here. And what we see is that as the shark is turning, one of the biggest movements we see is this very large depression of the pectoral fin. So that is movement about the, movement about the dorsal ventral axis. We also do see a little bit of pronation, so that's twisting about the medial-lateral axis. And then also some slight supination. So, I'm sorry, protraction. Yellow is protraction. So it's coming forward, supinating, and depressing. So having these videos are really cool, and now we know that pectoral fins are articulating and rotating about this axis. And I wanted to get a better idea of how these targeted muscles around the pectoral girdle are contributing to these kinematic outcomes. So I chose the three main muscles that are in the closely associated with the pectoral fin and the pectoral girdle. So this would be the dorsal pterygoideus, the cranial pterygoideus, or the protractor, and the ventral pterygoideus, or the depressor. And we sacrificed the shark and implanted these muscle bodies with electrodes and hooked those electrodes up to a signal generator to create muscle activation and contraction. It looks something like this. So that is the protractor, or the cranial pterygoideus, that's being stimulated in this video. And if we take this video, it was again calibrated for VROM. We can get another reconstruction. Okay, so again, the blue is going to be the fixed body axis, and the pink prism is the pectoral fin. So that's the motion we just saw in the video. We see that the fin is being protracted about that dorsal-ventral body axis. So we compared these motions across those three muscle groups, and we were looking again at the 3 rotational movements. So depression, elevation, protraction, retraction, and pronation, supination. And so all of my graphs are going to go by the motion, and the lines are indicating the different muscles that are being stimulated. So if we look first at elevation, much like you would suspect, if you stimulate the dorsal levator, you get a huge amount of elevation. Smells good. It's doing what it's supposed to. Interestingly, also though, when you stimulate the protractor, you are getting a little bit of elevation as well. So as that fin is coming forward, it is also rotating about the dorsal ventral axis. We did, again, as expected, see some slight depression when we stimulated the ventral depressor. If we look at pronation, which again is the twisting about the medial-lateral axis, we see the largest contribution to pronation is going to be stimulation of the protractor. So this lines up with those free-swimming kinematic videos we found, where we saw the fin protracting and pronating at the same time. Also, we see that if you stimulate either the dorsal levator or the ventral depressor, you will achieve supination. So in these experiments, we found that only the protractor would create pronation in this ventral fin. Then lastly, we looked at protraction, and this one is pretty clear. The only muscle that is creating protraction in the pectoral fin is the protractor. So the idea moving forward is to use these stimulation experiments in conjunction with these swimming trials to get a better idea of, again, how this pectoral fin is moving in 3D space, as well as how the muscles are contributing to those movements. So the big idea here, again, is, to my dismay, to unpair the idea of airplanes and sharks. So even just in casual observation, we see a huge amount of rotation in these pectoral fins. So I think moving forward, we need to think more about the rotational movement of these pectoral fins when we're thinking about rotational swimming kinematics. Because as the spin is rotating or abducting or pronating, we're not only changing the angle of attack to flow, but also the clear area to flow. So that will create all sorts of things like torque and different forces that are acting on the fin and causing overall different swimming models. Also with this project, we were very excited to get in-water GoPro VROM to work. So there was a lot of calibration and recalibration that went into getting a huge space, such as our 3-foot cubed volume, as well as dealing with these live swimming animals which don't do what you want basically ever. So poor Sam and I spent hours of our life in Fernald watching sharks pop their head out of the water, out of view of the camera. So I think this has really exciting potential applications to make it go out into the wild and try to get some true volitional kinematic data on some free swimming sharks outside of the constraints of lab space. And with that, I would like to thank my funders for helping me get up to this class, as well as our instructors, Dr. Summers, for all of your help, and my committee members who really pushed for this project, and I'm very glad that it worked. As well as Team VROM, JJ, and Thaddeus, and Giordano, as well as the rest of the fish class. And I would especially like to thank my co-authors who put so much time and effort and work into actually getting this going. So thank you all.
So I realize that things are very hot off the presses, but give a sense for what you would guess as to what the shark is doing in the volitional
Yeah.
in terms of what the muscles.
Right. So our hypothesis, as it has been for a while, and I feel that it is somewhat supported, is that as that fin is pronating and depressing, it's basically acting like a heel. What it's doing is converting all the sharks' forward momentum into support and basically whipping them around that fin.
And which muscles do you think you
No.
three muscles? Do you have a prediction about which one is the, are they all working? Is there one? Do you think there would be one primary driver or what?
I think in these turning videos and the turning video in general, I think the majority of the motion is coming from the third back. I think that the dorsal and ventral radius muscles will be more active during straight swimming when they may be adjusting their trim or other movements that aren't as exaggerated as this rotational movement.
Besides the muscles, similar so could you predict muscles and
It's a good question. So we'll see. I'm hoping so. There are some specialized species that will have subdivisions of muscles, like epaulet sharks, for instance, have three subdivisions of the thoracic muscle. So I think that plays a big role. And another big thing that we totally ignored in comparative, biomechanics of sharks is that there's a huge diversity of the skeletal morphology. So I think that is going to play a huge role in how these things are moving and how flexible they are, what degree of freedom they have to move in the articulation.
Okay. Okay. Thanks everyone for wrapping up our symposium here on
expanding the horizons of VROM. So I'm going to be talking about another application for it, along with some other things, looking at the expression or flair, if you will, of the sculpins and their defensive posturing. So defensive structures in fishes come in a lot of shapes and sizes, but generally they can be categorized into two big groups. Fishes are typically modifying the bony elements of their fins into big, robust spines, or they're typically modifying their scales into scutes or other kinds of sharp, pokey things. Another kind of modification for defense is in elements of the skull, and there's one group in particular that does this very well, and it's the sculpins. This is an Ophrys bison buffalo sculpin. The handsome gentleman there holding it and pointing out the spines was an Alaskan at the time. But if we look at the skull, you can see that there's all kinds of spines coming off of this fish, but most notably, really the most robust ones are all found elements of the operculum, the preopercle. The modification of the preopercle into this big spiny structure in sculpins is very diverse, very widespread. You see all kinds of different morphologies, all kinds of different levels of ornateness and robustness of the spines. But despite this seemingly abundant area for research, there's been very little attention paid to what the sculpins are doing with it and how they're coming to that end. So the purpose of my study was just to try and answer the question, how are these sculpins deploying these big preopercular spines? There's two big muscles that are attached to the preopercle, so that seemed like a great place to start. There's the levator arcus palatini, or the lap, and the adductor mandibulae. So to look at how these muscles are affecting the movement, we stimulated them one at a time. So this is stimulation of the adductor mandibulae. You can see that when it's stimulated, it does what an adductor mandibulae should do. It closes the mouth. Nothing too surprising there. And then if we stimulate the lap, the levator arcus palatini, it's erecting the spines very, very beautifully. And this is what we wanted to see. So to get an idea of what's going on underneath the surface here, we did some VROMing. And so what I have here is, this is a different species. This is an Ophrys bison, the buffalo sculpin. And it is erecting its preopercular spines, because some big scientist is poking in the head. And you can see that when it rotates the spine forward, it's also rotating the infraorbital series and kind of flexing them out. So what's interesting about this is that clearly the fish is capable of doing this motion just with the use of its levator arcus palatini. But there's got to be more to it than that. So if we just take this is a partially dissected Myoxocephalus, Polyacanthocephalus, and we bring back the hyoid by pulling on the pelvic girdle, you can see that it does a motion that is very, very similar to what we saw both in the live fish and in the Frankensculpin, where we activated the levator arcus palatini. So clearly this fish is not doing anything with its muscles, it's dead. And all of this action is being done by movement of the skeleton, just mechanics of the way that the bones are moving with one another. So if we look at the bones that are involved in this, you can see that this posterior movement of the vasobranchials, which are connected up here towards the hyoid series, when those are moved posteriorly, it basically folds out the hyoid series, and this movement, this lateral movement of the hyoids, pushes these preopercles out and erects the spines. And another element that's involved in this, so here is that partially dissected Myoxocephalus. with a little more going on than it had in previous slides. This big bony element right there is a bony extension of the infraorbital series of the suborbital stay. And you can see that it's connecting right to the base of that big uppermost preopercular spine. And if you look at if you kind of combine that with the movement of the hyoid, where the hyoid is actually pushing on the preopercle when it flares it out, you can see that the suborbital stay is connecting right here in kind of a little groove that's at the base of this spine. And in the back, this preopercle is getting pushed on through a series of connections with the hyoid. So you have, on the inside of the fish, this hyoid pushing this preopercle out, and on the outside of the fish, you have this suborbital stay in the infraorbital series bracing it on the front. And my idea is that this brace is a way of maintaining structural integrity when the fish is actually using these spines in real life, whether it be for defense or for offense. You can imagine that simply flaring something out with muscles would be certainly improved if you could brace the entire structure simply by the mechanics of the skeleton. And interestingly enough, the suborbital stay in sculpins is very well attached to the adductor mandibular, the jaw muscles. And you probably can't recall it from the video, but I'll just describe it for you. When the sculpin in real life is erecting these preopercular spines, you can see it clench down with its jaw. The jaw is always closed when they do this. And so if you have an adductor mandibular that's attached to this suborbital stay and it's clenching its mouth, it's rigidly pulling down that suborbital stay and keeping it right in that little pocket where it needs to sit to form a rigid structure and brace the entire system when they're in that posture. And to my knowledge, this is the first proposed function of the suborbital stay in any fish, but please correct me if I'm wrong about that. So in conclusion, sculpins use their spines certainly for defense, possibly for offense. Regardless, they need them to be in place when they're using them. If they're being bitten down upon by a bigger sculpin or some other thing, they clearly don't want those spines just folding back in place. You can see here that this Myoxocephalus being eaten by this red Irish lord, that these preopercular spines are just catching on the edge of the jaw. Now, what the future lay and hold for that poor Myoxocephalus, we cannot be certain, but at least he's giving up a good fight. So with that, I would like to acknowledge all the groups that gave me money so that I could come out here and take this wonderful class. It's been a huge pleasure, and it wouldn't have been possible for me to do all this work without the support of you all. But I'd especially like to thank, in alphabetical order, Sarah, Samantha, JJ, and Diego for many hours of help and philosophical musings. I'd also like to thank Beth Brainerd for helping me extensively with getting the VROM animations to work and all kinds of other sewing and other suturing of the little sculpins that we use. I'd also like to thank the instructors, Adam and Alice, and of course, Chris Pratt, wherever he is. I'd like to thank him as well. And I'll take any questions.
So the suborbital stay has broader fibers. Do you have a similar kind of thing?
I don't. So I dissected a bunch of hexagrammata, a lingcod, and 2 species of regular greenling, a rockfish, and just for good measure, it's not a scorpeniform or formerly scorpeniform, but cod. And in the rockfish, for instance, rockfishes also have preopercular spines and not nearly as robust or innate as those seen in sculpins, but they're very, very sharp, and they're clearly using them for something. But the suborbital stay in rockfishes is this just pathetic little thing that drops down and kind of fizzles out in the middle of the cheek. Interestingly, there's a couple of sculpin species that the suborbital stay does not go all the way to the back, but if you erect out their spines, there's such a huge movement of these spines that it actually moves it into place and locks in by this kind of anterior flipping motion of the preopercle. In greenlings, which is a great outgroup for sculpins, the attachment of the suborbital stay is not nearly as robust. There isn't the big kind of tendinous connection with the adductor mandibulae. It's attached, but very, very lightly, and it's very easy to disconnect. And instead of it being kind of fitted into a little bony groove, it's kind of hanging over the edge and kind of attaching like an afterthought. And I think this is a unique role for the suborbital stay, given this unique and highly specialized movement of the preopercle, which is an element of the operculum, obviously. And so you don't lightly start messing around with the bones you use to breathe typically. So, yeah.
Do you see fish?
So that's a great question. So in Myoxocephalus, for instance, when I was trying to decide what species to do with VROM, we had a bunch of Myoxocephalus, one buffalo sculpin and some Leptocatus. They were all great candidates, but the Myoxocephalus, I noticed, had a very different behavior from the Onofriates. Even though they're closely related, their skeletons are very, very similar, their spines are very similar. But when you pick up a Myoxocephalus, it doesn't go into this big, I'm just going to sit here and stick out all these spines and wait for you to go away and learn your lesson. It actually just kind of flips it out and tries to stab back at you. And the hard way, several times. I didn't take no for an answer, but then eventually I caved. So I think that there's a big behavioral element, and I think that any one fish is capable of deploying these spines in multiple ways. So for instance, if they just use the muscle to pull that spine out, they can use it maybe for quick stabbing motions like Myoxocephalus. But if they're clearly in duress because some scientist is holding them completely still and they know they can't get away, then they'll go into the full flare-out kind of motion. And I think that they don't do that lightly, because every time that I've seen it, before they do it, their bones are all inside their skin. And after they do it, all the spines have come out of the skin. I think it's not something that they really do if they can get away with not. What? I did, yeah. And it looked virtually the same. I have some high-speed video of it, though, and I'm really eager to see whether or not you can detect any movement of the suborbital stick.
Okay, thanks.
Not that one. So today I won't talk to you about reproductive structures in perch. Instead, I'm going to talk to you about these other really cool structures. I've become familiar with them at my time here at Friday Harbor, the pharyngeal jaw apparatus. And so what they are, the pharyngeal jaw consists of the lower pharyngeal jaw and the upper pharyngeal jaw. So it opens its mouth, food comes in, crushes the food, grinds it up, and then passes it to the but there are morphological specializations that can occur, so differences in the jaw that can lead to resource partitioning. So in the surf perch, there is a lot of evidence of resource partitioning. We typically see generalists, and they're going to have a different shape jaw for the type of food that they eat. And we also have specialists. So for instance, this image here is a Retrocylus haka who ingested a bunch of little mollusks that you can see in the digestive tract, as well as herbivores, or other specialists like herbivores.
So how did they do this? Well, the third part are pharyngeal, I can never say this word, pharyngognathy, and they had a single fused lower pharyngeal jaw, which is attached to the neurocranium by the muscles on the side, creates a sling. But you also have this joint that is dorsal to the upper pharyngeal jaw, and then so the upper pharyngeal jaw is going to be rotating, and this joint allows for maximal rotation. So I think my favorite part about the third part is that they give live birth. So we know that there's resource partitioning in the adults, but my question was, well, what about the young? Are the young also resource partitioning? And the answer is actually that they do. Jeff said that I've been working with the juvenile Rhacophyllus vaca and Embryonica lateralis, and he's been looking at gut content and found that the Rhacophyllus vaca, again, which is a specialist for mollusk crushing, found a higher average of shell in its gut compared to Embryonica lateralis, who is more of a generalist. So I was more concerned with the morphological aspect of it. So are the Rhacophyllus vaca, the juveniles, more morphologically specialized to eat those foods even right after birth? So I looked at juvenile Rhacophyllus vaca, again, a specialist in mollusk crushing, Embryonica lateralis, again, juvenile, but is more of a generalist, and then added Cymatogaster abrugata, who again is also a generalist. So we went out, we collected our perch. They'll never let me row a boat ever again. We used some CT scanning to look at density, some clearing and staining, so we can look at ossification, dissection, so we can look at the muscles that are associated with the pharyngeal jaws, and also try to do some prediction of muscle force. And how we did that is, and you can see that muscle that the code is pointing to, it's kind of like conical or cone shape. So we use the volume of a cone, in addition to an average of muscle fiber length within that muscle, divide the volume by the fiber length, with a constant that we got from previous literature to get a total force in that muscle. For more complex muscles, we took connection into consideration. So in addition to volume and fiber length, we also looked at angle and then a few trigonometric later, we were able to determine total force. So the first thing we saw was that the density in the mollusk crushers, the Rhacophyllus vaca, was significantly higher than the density in the upper and lower pharyngeal jaws of the generalist Embryonica lateralis. Now, what we do see, however, is that Cymatogaster abrugata and our vaca are not really different. And this is because even though Rhacophyllus vaca and Cymatogaster abrugata were very similar in size, Rhacophyllus vaca tends to be slightly bigger. So Cymatogaster was probably a little bit closer to being an adult. So the Rhacophyllus is more closely related to the adult, closer to the adult. So here I just wanted to really give you an idea of what the jaws look like in the mollusk specialist and then the generalist. And the biggest difference we can see here is the robustness of the lower pharyngeal jaw. So that's a lower than that compared to the lower pharyngeal jaw, but I guess that's that. Another thing that we were looking at that we can tell here is I made some 3D models of the pharyngeal jaws. And anything that has pink in it is the location and where the muscle attachment goes. And there's a clear difference between the two. The mollusk specialist has a greater surface area for muscle attachment, so it's going to need more muscles to generate more force to crush those bones, and then the Cymatogaster abrugata doesn't have that much space. We also looked at the pharyngeal apophysis, and that's just, again, the joint that allows that maximal rotation of the upper pharyngeal jaw. And we're just getting a general view of it. There is a slight difference in size, but we haven't looked at anything yet. What we did do is do some clearing and staining and found that the structures are fully ossified in all three of the species. So Brachypeltis vaca and Biotica lateralis, again, are the juvenile species, and they are fully ossified compared to almost adult Cymaticraptor. Similarly, we also look at lower pharyngeal jaw ossification, and it picked up the red stain, which is stain for the bone in all three. So the juveniles are not different from the adults. And I also looked at muscles. So later short, later sternivore, later posterior, the tractidorsalis, which are all involved in the process of pharyngeal jaw movement. So that's why I focus on those three muscles. And what I found was, not only did I dissect the three levator, posterior levator, sternivore, and tractidorsalis, I also dissected out the A1 and A23, and these are all associated or found within the cranial region, and did not find any significant difference between the percent muscle among the three species. But when I focused on the other three muscles which are associated with the jaws, we found that the Brachypeltis vaca had much larger jaws compared to Cymaticraptor and Amygdala and Biotica. And also looking at force, we saw the same trend that Brachypeltis vaca had able to generate a greater force compared to Cymaticraptor and Biotica. And so what we were able to determine is that yes, the juveniles are like miniature adults. They are specialized right from birth, so they have dense jaws. And this is specifically looking at Brachypeltis vaca, so the jaws are denser. They are bigger. They are fully ossified. They have larger muscles, and they have greater force that they can generate with those big muscles. And with that, December, sorry. And every single one of you provided me with help, whether it was with CT, with 3D modeling, with Clarion staining, with everything. So thank you all very much.
Questions?
What about the
That I didn't really focus on. The only thing that I could really tell you is that the teeth in the Brachypeltis are much bigger and robust compared to the other ones. And I'm assuming that's just a greater surface area to brush the mollusk. But I haven't really looked any further into that. It's just a shape and they're bigger. Yes.
Are there any diet studies that you know of that focus specifically on the arrives to purchase?
I don't know. That'd be really cool to look at. I really, really wanted to get that gravid female and see what those jaws look like. But if not, I don't know for sure. No, I think you asked me that, and I couldn't see it. No, I looked at the bottom and then the sides, but I couldn't pick up on any secrets. Good. Okay, thank you.
Oh, I think we should pick. Yep. We got a 3-minute deep breath to get us back on schedule since, let's see, what do we got now? We're down to 14 viewers. We were up at 19 a minute ago. But we're definitely being viewed in Saudi Arabia. Todd Clardy, a former fish class student who's at King Fahd something. Maybe Matt Tinkle was as well. I don't know. He's at KAUST. He's at King Abdullah University of Science and Technology. I might be I might be able to see who if I started pushing buttons, but the last time I pushed buttons, it shut everything down and I had to like erase everything and email out new links. So since there's probably several people watching just to see Yanni would be unkind. Yeah, I'm getting things from Philly. People are watching in Philly and in the Midwest. Where's University of Southern Indiana just tuned in.
I thought we had a rock that was carrying down. So, you know,
Did it spit it out?
no, we just didn't around that way. We just inside.
Yeah.
Seemed like the wrong place.
All right, Yanni. All right. Next up is Yanni with the longish last name.
Longish last name. All right. So we'll talk about my research on scaling with armor and northern spearnose poacher at Tulsa. And as many of the students already alluded to, fish have spines and that kind of cool stuff. So I'm just gonna jump directly to steal something there knows that the ocean is dark and full of arrows and there's specific armor for that. So many fish have evolved different ways of defending themselves. There's I'm going to show specific examples of thermal armor. We have a catfish right here, very cool gar right here with gadite scales. And then some of the newer and hotter topics, Paraplima scales and the seahorse tail. So the material properties of the scales of the leg and morphology of those scales and how they're aligned with each other has really brought some really interesting bioscience research into how to make better armor. But also, this is just really cool. I'm pointing this out because I'm going to come back to this later in the talk. The seahorse tail square has this force strut scale on the side, and the reason that it's square allows them to want to better wrap around objects. And also, when it's deformed, it's easier to bring it back to its normal form. So I'll get back to that later. So armor is really cool, but as I mentioned, the ocean is pretty terrifying. Let's skip this slide. Oh yeah. Yeah. I'm not going to talk about scaling because we've talked so much about scaling, but I want to mention ontology in fish. I brought some of this work really small. There are many morphological different changes, and some fish, when they larvae have spines and they lose them as they grow older, but some have defenses all along throughout their life cycle. One of the animals which has armor. So this is more of a poacher, also. Top left is a 3 centimeter specimen, which my lighting is fun. He's guys have modified scales which are derived from which form bony plates. And most of them have poly-oriented spines, which in fact is one of the things that probably dull with discomfort, but it's pretty cool. What's really neat is they don't have swim bladder. So they have this armor, and when they're adults, they're bottom. When they're juveniles, they swim around in the water column every now and then, and they still have armor. So from this S pattern, which is also probably going to bring some bad memories to the quiz. Yeah. And just to drive this point home, this is the same fish I had in the top left, CT scan. You can see the armor right here all over the body surrounding the fish, giving it protection. One of the big questions is how does a fish like this, what changes as it grows from a small 1 centimeter fish to full adult size at 60, 70 centimeters. So the research question is how does armor scale with body size? Also, I want to see how the armor resists compressive fluids through touching. So we collected 15, and I mean we all collected the fish, it wasn't just me. We had 15 specimens of Meganopsis balsa, and they were kept in the lab until they unfortunately were euthanized for scientific purposes. But we collected them through trawling, night lighting, long night lighting actually, and beach seining, which was awesome. And 9 specimens were used to image the scales, so the animals were preserved ethanol. And in each scan took place 2 samples so we can get bone mineral densities out of all the specimens we scanned. And then 6 specimens were used for material testing purposes, so they were not preserved anything, they were just put in the freezer in a straight position until ready to be experimented upon. I'm going to start by talking about the scaling, and we're going to get a ton up there, the scales of interest. There's a lot of scales on this fish, a lot of armor. I know I look at it all, but focus on the little area. We only have 5 weeks. So I'm going to look at that area right there, right around below the second dorsal fin. And I'm going to zoom in. And look at the 2 top rows on the left side of that, so that's the dorsolateral row and the superlateral row. I look at 3 scales of each of the rows. For these scales, I digitize the volumes and also the bone material densities. So bone mineral densities. And then I scaled those with body size, and as you know, when we do scaling studies, we can put slope. There are certain slopes which animals scale with, so we can say that they scale asymmetrically with something, or that there might be some disproportional scaling when they don't meet those requirements. So my hypothesis was that bone mineral density and armor volume will scale asymmetrically with body size, and the slopes for this are 0 and 3 respectively. Now I'm going to baffle you with some data. Right now I'm showing you bone mineral density and percent hypoxia appetite. The y-axis, these are log adjusted scales. I have my fish in the bottom, the x-axis shows the size differences. What we see is we have a linear relationship bone mineral density at some 0.4. And I could test and check if this is different from 0, but since it's already significant at 0.31, I don't need to do that. We see that this slope is definitely different from 0. Next up, showing the armor volume. Same again with the log scale, x and y axes. You can see again a nice linear relationship with a slope of 0.2827. Do the t-test to see if it's different from the slope of 3, and it's not different, so it's scaling isometrically, which is very nice. And that comes in the cool part. What happens with compressive loads? So this here is a cross section of this region of interest. It's the 19, 20, and 21st scale of the scale of interest. We have 8 bony plates which surround the animal. If you remember the sequence, it has 4 plates surrounding it. So this is definitely a different configuration to resist loads. So what we did is we did dorsiventral loadings throughout the blue, and then we did ipsilateral loadings in the red arrows. On the right, we have the material testing system, which I used, and a little chunk of fish in there, which I was testing. So I couldn't just put the whole fish in there, you see I have a chunk, so I divided the fish up into 9 regions. First region is the head. Didn't want to switch that, that would be fun. But I did the rest of the body, and along the body, these are very cool differences. Anteriorly, the second and third segment, the animal has ribs, which attach to the side of the armor. And as we go further down, toward So at the tail, we have the neural processes which go in dorsal-ventral direction in the animal. So we can hypothesize here what might happen when you put dorsal-ventral lateral loadings. What I hypothesize is that as size increases, more forces are trying to achieve 60% compression, because that's what I did. So I compressed every segment to 60%. And those segments which have ribs, I hypothesize they will withstand ipsilateral loading because they're going to the side. So we can take a little more force to crush those. And also those segments which have those neural processes going in dorsal-ventral direction, those will withstand dorsal-ventral loading better than segments which don't have it. Now comes the fun part. Here, after I crushed every segment, I put those segments into a lyophilizer, freeze dryer, and I scanned it again. So these are scans of the same regions of interest after I dorsal-ventral corrected. You can see that the scales are still in place. There's a little bit of bending up there, but the most damage is the neural processes around the people. It's interesting, most damage happens there, but the scales that do not slide like with the seahorse, so these are, they stay in place, so it's more squishy, gives a little more in. And I'm going to show you with the data here. So this is a size series. So here I have my dorsal-ventral loading, and I did 3 animals for dorsal-ventral loading. And we have size series which go from 100 millimeters up to 140 millimeters in the center back. And what we see here is looking for a pattern. I don't see any pattern. It looks like it's all in place. So this could be for many reasons, but there's a likelihood that there will be operator error, but you never know. But it's really interesting to see the differences here. But when we put the ipsilateral compressions, we see patterns. It's very cool. We see that the smaller animals require less force to get those key loads. The bigger animals require more force to get there. Also, we see that these segments right here, this is the 3rd segment and the 8th segment, require more force than the other ones do, or they have more, they can take more load. Which is interesting because the 2nd and the 9th segment, they look very similar to the 3rd and the 8th segment. I will show you that in the next slide. So here we have cross sections of the 3rd and the 8th segment. You can see the ribs right here, and the neural process up there, and here's the 8th segment. These two would help the most load. We'll look at those patterns. But then it's interesting to look at why did those other segments, which look very similar to those, why were they doing so poorly? So I put those down here. First thing which comes to mind when we look at the second segment is that these ribs are much more ventrally located. Also, which you cannot see from here because it's a CT scan. But there's also a big abdominal cavity, which is a little bit switched here and gives you more load. Here's also an abdominal cavity, but it's much more reduced there. And here, not sure what goes on there. The shape changes a little bit, but I think there is some really cool stuff which can be done to look at why this configuration is more stable than that. So that's what I did so far. And when I get to my acknowledgement, I want to acknowledge one frame of mine. It's hard to see, but there's a little worm right there. Parasitic worm, which pop out of the fish segments, which I was crushing. So that makes for very sleepless nights. I think I grossed all of the odds. Hey, there's a worm on the bill. But yeah, but the people I really want to thank is all of you, fish class. You're awesome. Instructors, you're fantastic. Exactly, I'm sorry, I'm so annoying. And I really want to thank my wife Nicole. Letting me come here, she's at home, take care of all the chores while pregnant, so that husband, I'm home. With that, you have any questions?
If section 2 is right there, particularly down it might be more protected, by ordering the kind of
It's not, it's right posterior to the head region. The head region is very strongly armored and all that things. I think there might be some support coming from the anterior region. Since I cut it into segments, it's not there anymore. be nice to squish whole fish, but they don't do it.
But do you think you're missing anything by just looking at circuits? Like if you're doing more support, like it's kind of could be like missing off.
Looking at the whole body.
Yeah, like are you
I'm not doing it, yeah, I think so. I just wanted to regionalize the animal. It gives you a different idea of how the morphology is in insects. Put the whole fish in there, it's supposed to synthesize and like take much more force, but then when it fails, not much of it.
Well, the idea that these projects are like organic, and sort of one thing and another thing, but you did start out at some decking, you ever get a sense for how much the farmer and their own observation scales and everything?
It's so Sarah's going to talk about that a little bit. What I saw in this, and what I really should have done is I should have split this over. You can see that there's some overlapping of the scales, so it doesn't look like they're sliding too much. It seems to be more than just better than some more independent in context of the motion.
Maybe, is there any kind of regionalization of the body? Like when we swimming, is there particular areas that move more than the rest of it, or is it pretty much like the whole body?
And maybe it's held by coral swimming, motion as far as I know. But maybe some bird swimming. But that no, they only have a most of the you gotta have a great talk.
Send me up nice.
I think you said time out. 20 seconds.
think there's any shear force that you guys
I wanted to do some extra posterior loading, but I ran out of
I know, I guess if it's really good,
So I did my project on puncture force scaling in flatfishes. So I'll start off talking about fish scales. So they are incredibly diverse and incredibly amazing as well. So most of us know the major types of scales. There's cycloid scales, canoid scales, placoid, and then the few fishes that have ganoid scales. And then what I was interested in is one of the weird fishes we had in the lab that had these Hercules scales. And they have some better pictures of that. But these scales can differ in individual fishes, across ontogeny in different areas, and obviously across phylogeny, where sharks have placoid, the gars have ganoid, the helias have these, and then weird. I was also interested in the flatfishes. I think they're a very interesting group. They start off as a bilaterally symmetric larvae. One eye migrates from one side of the body, right and left, to the other side, and what you're left with is a fish with two eyes on, in this case, the right side of the body, and the left side of the body with no eyes. So it'd be the blind side and the eye side. Given that these fish are flat, you have different functions for different sides of the body. So the blind side is usually in contact with compressed substrate. The eye side is usually either exposed or slightly covered with a thin contact substrate. And it is the scales, skin and the scales, that are responsible for a lot of these functions. And one of the major functions of why they vary is to be cryptic, to hide the predators or to ambush in some way. So you get this crypsis type of effect. But I was interested in puncture force. So using puncture force to model some sort of predation. So the species I used, which were the ones we caught a lot of, and the size range here were Proceculus, Pledictes pilatus, and Isopseta isolepis. And this was the one that most interested me when we got them in the lab and we were pulling them out of the seine. I was picking up and they felt like sandpaper. They were incredibly weird, and these were scales that were making them weird. These guys feel just like normal fishes, and they came out of the trawl, so muddy substrate. These guys were in kind of a rocky area. So differences in habitat there. All right, so for puncture force, I had the idea of these guys have tough skin, tough scales, these guys don't. So I have the analogy of if you were going to bite into an apple, that's what these guys would be simulating. And then if you were to try to bite into these, I think it would be more like biting into an orange. So you're not going to bite into an orange and get all the nice juice in it. You're going to have to peel it first. So we have some differences within what the predator could be experiencing. So this led to my questions. So how does scale morphology change across flatfishes? How does puncture force and scale morphology change over size ranges? Are there differences in puncture force for the eye side and the line side? And then what factors will contribute to increased puncture force? Okay. So here are light microscope images of our different fishes. So the Pterophrys have cycloid scales slightly overlapping. The Pledictes have these beautiful trabeculate scales that don't overlap. They're usually fairly spread apart. And then the Isopseta have penoid scales overlapping, usually much larger as well. I also took some SEM images. So I took the SEM, tilted it 45 degrees to get an idea of depth of these scales. Pterophrys and Isopseta are fairly flat, very thin scales. And then these are just super weak. So they have a lot of depth to them, and then they have all those projections. So looking at the scale morphology in size matched individuals, here in the green boxes we have the density of scales, how many scales are in a particular area. And then the purple triangles are scale diameter. So a measure of the size of the scale. So up here we have these high densities, which are cycloid scales, high density but really small scales. Isopseta is kind of the intermediate for that, and then Pledictes have very large scales and very low density. So we're getting differences in scale morphology. The next thing was the puncture test. So I used the MTS. So here's a diagram of the MTS. What I did was I skinned both the eye side and the blind side, stretched it on an apple, pinned it in place, and then this pin came down and would eventually puncture through the skin. What we got was output. So extension is how far that pin is going down, load is how much force, and then you get this drop in force. That is where the pin would break the skin. And that was the force I used. So the idea of scaling is you have the two possible outcomes. You have isometric scaling, which is increase in size with increase in, or the proportion staying the same. Allometric scaling is when you increase in size, the proportion changes somewhat. And it's been alluded to there are scaling relationships and scaling exponents that I'll be looking at. So the first thing I want to do is I lumped all the fish because they had the same relationship for this. I plotted standard length on a log axis, mass on a log axis, and looked at how these fish get scaled to each other. So you would expect mass to increase with the mean of length, and that is just about what we observed in sort of have isometric scaling in that case. And then I started looking at puncture force, and here I have eye side in orange, blind side in blue, and what we got were scaling exponents. So in this case, blind side and eye side are scaling to the same exponent in Pledictes, and it's just about the mean scaling. And then I compared taking the average of the forces for the eye side and blind side to see if there were differences, and there were no differences. So in this case, we have linear scaling, no differences between eye side and blind side. Isopseta, we actually have sublinear scaling, so 0.63, 0.49. and still no differences in eyesight and blind sight. And then the peripheries, again, no difference in blind sight and eyesight, and slight differences that I don't think are significant. And I would consider them to be more than the scaling of the function. So the next thing I wanted to do is try to relate this to how the scales of skin are actually changing in these size ranges. So at for the scale density, which is an area measurement, we have an expected what we would expect for the change of these size ranges, and that would be the negative square length, and that is exactly what we observe. And I'm only showing it with these, but it's the same relationship in all. And then I also took the area for each scale, and we got the exact same relationship. You'd expect it to increase the square of length and decrease the square of length. So since we have these differences between puncture force, especially between eyesight setup and Plutichtes, but no changes in the morphology that I'm measuring, I'm not measuring the right thing. All right, so a little bit about why this could be occurring. So here were our apples, and these were the ones that we found in that muddy trawl. Guys are relying on cryptids to avoid predators as opposed to beefing up their scales to increase puncture force. Well, these guys are in a way getting armor. It's interspersed, but it does increase their puncture force. So the summary of these guys was we have linear puncture force in these cases, sublinear in this. The things I measured, there was no morphology that I could use to explain this at the time. And across the board, there's no differences in blind sight and eyesight. So my next step in this is to look at what I think may be responsible for this is scale thickness. So even within the scale or across different types of scales, they could be variable thickness. And that's why I brought these SEM images back. Here we have our isopseta with their incredibly thin scales. These guys with their much thicker scales, much higher puncture force. So what I want to do is, and I have this sample, look at the thickness of these scales over these size ranges and see if that correlates to the same scale that I'm getting in puncture force.
Well, if one is in the rocky habitat, is there going to be some differences in their ability to vary in the substrate because of differences in the scale?
I'm not sure about varying in the substrate, but in terms of keeping substrate on top of them, studies have been done in that, and it seems the more projections coming out of the scale, so those spikes coming out of the Plutichtes or the penny coming out of the isopseta, those seem to help substrate on top, given a certain size range. If you prefer a particular substrate size that matches.
What is going on?
So I only showed the eyesight because I haven't analyzed the eyesight yet, but it's the same species. Some flatfish have differences. They don't have pendulum scales on the top, cycloid on the bottom. So if they had cycloid on the top and cycloid on the bottom, they had those divergent scales on the blind side.
So this is going off of the idea that some have different types of scales on the eyesight versus the blind side. If you found the puncture resistance to be the same on eyesight and blind side for these, why would the different flatfish need different types of scales?
So these scales are not just evolving for puncture force or puncture resistance. There's a lot of different things. I think that may have to do with keeping substrate on top of them while being able to be a little freer to move from the wrong side, things like that.
How much of a difference between apples and orange is like the bottom of so if you live in a rocky area and
So hello, my name is Claire Fox, and my project was on benthic walking and flatfishes. So as you know, there are many benthic fish that perform something akin to walking, and the primary benefits of that are that compared to foreign body undulations, it can be more energy efficient. Also, you can remain more focused, so like on the other produce pressure waves that can be sensed by predators and prey. And lastly, if you're a predator, the flatfish that I studied, being able to maneuver and push yourself off the substrate and help you replace that between yourself and the prey item rapidly. So I was excited to find that benthic locomotion in flatfishes has not been described in the literature. So my primary goals were to do the actual description and begin some analysis of the kinematics of what's happening. So one interesting thing is that when you start to describe something for the first time, you have both a privilege and a challenge of finding the appropriate terminology. So because you guys have been staring at people talking, I'm going to invite you right now to throw out some words about what you think you might be seeing there. So this is a lateral view. So Adam is fond of saying that flatfish are two-dimensional, but a very key component to analyzing what's happening here is actually going to take lateral video. Does anyone want to throw out some words? Is this walking, first of all?
Scurrying.
Scurrying, yeah, it makes sense. Tiptoeing?
Follow the leader.
The leader? Oh yeah, because you have one way, one way.
I don't know how strong it looks.
Okay, so someone's saying millipedes. There was someone who started to investigate this and never got into the paper stage, but that was the first question they had. The hypothesis was this is similar to a millipede gait, and it turned out that it really isn't. And if you notice, if we look at another lateral view, this fish is moving a little more quickly, and it's moving to pretty subtle movement. But you can see that there is no undulation in the body at all. It's very different from how they swim. And they're just sort of creeping along. And the way that I chose to describe this is that there are waves of bunched medial fin that are coming together to form a kind of functional foot, which is pushing backwards. And this foot is sequential. So different regions of the medial fin become the foot as we move backwards. And so I don't really get into the waveform like that is because these waves are actually pushing against the substrate. But the idea is that so I chose to look very closely at this one walking sequence from Pithecus monostichus. And this is because they walked very lightly and they were reasonably cooperative. And this particular species, you can see that at the very beginning of one wave, as it propagates this way, the previous wave is just ending. So at different points in the walk cycle, you can have one wave. So from the side, it sort of looks like 1 foot, and another point in the walk cycle is looks like 2 feet. So coming in closer for a detailed look at what is happening, we can track a single fin rate for the walk cycle. So it's sort of in the western state, it's at 90 degrees to the body, and in the first step, it swings forward. So this is the anterior side of the fish. So the way it swings up and forward to the end of 45 degrees, and then it joins this backward whirl. So actually, the anterior most part of the wave is pushing down and under, and this part is turning over. And so it travels backwards around the body until it reaches an angle of about 135 degrees. So one curiosity is not only that they're using this long medial fin to form a sequential foot, but also that they are using medial fins as feet. So as Mike mentioned, there's this axial transformation that happens during metamorphosis in flatfish. And as far as I know, this is the only fish that propels itself along a substrate using fins that are typically associated at the top and the bottom of the fish. So one interesting challenge that leads to is the fact that these are not symmetrical fins. So you can see that the anal fin stops quite short, whereas the dorsal fin is very long and goes all the way up to the head. So I found that 37% of the dorsal fin is not used at all in propulsion, and that the way it starts, right about here on the page in the middle, it travels backwards. And so this portion isn't used at all. So the actual portion that we're using the wavelet is symmetrical and it's parallel. And so I did a test with 10 fish, and I looked at them at 3 points in the left circle and a big circle at the beginning and the end, and I found that it was essentially 90 degrees and that they are so I spent most of my time at Friday Harbor nudging recalcitrant flatfish into walking because they really want to be cryptic. I'm into the sand and you can't see me. So that took the majority of my time. And I wanted to have a lot of videos to continue to analyze and get the quality of information. So I didn't really have a lot of time for quantitative analysis, but I did analyze every shot through tracking on an initial 10 individuals, 25 walking sequences. And I chose to focus on 50 and 40 specialists. And particularly is sort of my model walker, and Clover is my model bounder. I also found that some of the fish was a bounding gait. And I looked at 6 species, and I found that they all are capable of walking, but that some of them do it more than others. Some of them prefer to bound, and some of them move more directly into swimming. So I found that the wavelet scales into functional length of medial fins. So no matter what the size of the fish, the wavelength is going to be either equal to or just shorter than the anal fin length. And I found that the frequency ranges from 1.4 to 2.6 cycles per second. And I found a minimum frequency for steady walking was 1.4 for strong cycles or smaller, and 2.8 for long centimeters or larger. According to my reservoir. So these are the mesmerizing sequences that are interested in. And you can see that with this individual, you can see that the beginning and the end of the wave cycle overlap. And my hypothesis is that's what enables you to get a really steady walking velocity. It's pushing off and then gliding, slowing down, pushing off and gliding. But I think that this area is going to be shorter and probably less able to, has less surface area to contact the substrate, might be able to produce less thrust. So when the wave cycle is shortened, so there's that overlap, I think that there's probably going to be equal amount of thrust happening to that walk cycle. So this is in contrast to the protein speculus. And this individual is going to be showing as bounding. So the bounding is kind of like toe hopping, where they push off in parallel for fins, and either glide or actually break. So if you look at the pictures from the side, sometimes they swing their fins forward to stop. So that fish is trying to decide whether or not to eat their probe. So they're generally doing this, to investigate their environment. I've seen them hop forward and bite it. And you can see the velocity at the time. So to close, I'm very excited about this, seemingly unique form of motion. And when you encounter something like this, you can ask the question, well, is it unique? Is it showing up elsewhere in other taxa? And Adam suggested that there's this form of wave that is used in rowing, in internships, and instead of rowing all oars backwards at once, it's actually more efficient to start a wave that travels down. And it's similar to
And these are mitochondrial wave patterns in mitochondria. And so the cilia, there's a lot of growth in the cilia, and all the growth in sequential waves. So I'm interested in maybe building, little robot factors that can walk around on the substrate. So yeah, I'll be moving forward with this project. And the first thing I want to thank everyone as a non-traditional student and someone who's not I appreciate all of your patience and how helpful everyone's been in my project. And particularly Mike at Concentrated Pice and the Initiative Established, and Alice for introducing me to the research foundation. So, hello.
I think you guys have a very representative. I thought about the war center perhaps having them up to the front, they're pushing towards the middle, so maybe it's easier to pushing sideways, pushing forward on the back. That's the kind of like,
I have not thought about that, aside from, thinking that if we use the front surface, that it's going to end up having more rest on that side. But I also have an essay on the citric peas raised in the very front. If you remember, they have like the mohawk with the 3 rays. And so we think that they could have a sensory function. So I haven't gotten pictures from that yet, but it may be that they're freed up from the locomotor function of more of their sensory. Yeah.
You can see the consistency that
We could just keep going with the favorite density investigation. Sure, now that we've perfected, now that really perfected.
I'm looking for the shapes of the boundary versus the.
Yeah, there is. And in the boundaries, they form a little more of a triangle, like they're a little bit of triangle, right at that midpoint of the body. So yeah, and there's so much analysis that can be done on the direct.
I just noticed watching the property move around, but times I saw them move their more anterior fin rays, and when they were turning, they would pivot really fast. And it would be a perfect impact on that surgeon. So that's interesting.
It seems like you're coming on walking on class.
Yeah, that is definitely something that I need to try. Because I don't know if you noticed, but there's a lot of slippage, and I did calculate that the velocity of the thing that is 3 times that of the velocity of the body. So there's definitely loss there that's happening. And so that's one of these things that I think is very handy for this session. I'm going to try to squeeze in some more filming and filming them on national campus. That was the first thing I said when I started the project. Is like, I have to film them on sand. Yeah.
You guys reverse employee?
They can. They back up, and they also do fantastic vacations. They do the things. So yeah, I have a lot of videos backing up.
A knife fit. With somewhat kind of motion, because it was simply, simply down the same thing,
Definitely
right?
same motion, but that was done in a hyperdynamic context.
Ah, right.
Right? This is
Yeah,
done.
it's not walking.
This
It's not
is
walking.
done,
But this is the same structure.
It's hot. Me? No.
I'll jump in here if it's a bill. See how much.
Or she's just.
She's been tweeting, so I think she. Yeah, I think she's watching. Ah. I don't know how different the Hector girls look. You know, there aren't very many.
No, I didn't know they were taken.
There are, but there aren't many. New version?
Yeah, I got some nice here.
Hey.
Yeah.
You want to talk about that?
That's just easier. You get drive it.
I mean, you know, like a lot of the terminology that I have to learn
so
now, but I can hold it on the staff. I'm really good at the research method. I can really kind of, no, but I'm I'm used to experience,
I teach. Of course, it's your favorite song. I teach. Follow it. A lot of hours in the day.
a lot of emotion, but it sounds exciting. Oh, that's what I would, that would be. Do we have some more?
Yep.
Great.
Yep. And, Sarah, Rodano, Sam.
And tomorrow's.
Tomorrow's
Tomorrow's clean up and right on. Oh, this is time you get it. Pretty good, huh? The quality of talk
So that can run usually after 10 before noon. And then, yep, and then after 1:30 before.
So I was gonna put it on.
I'll just download it.
Okay, yeah, I have a PDF. I figured
You're
out.
saying that this is
I
not.
don't think I have anything. I've been not paying any attention to next week's calendar because of this.
Yeah, I figured out how to export the scan.
I've got nothing.
So next.
You pick it.
Okay, let's get it. And then one of the girls is gonna do some things on moving around, do the reproduction. I think it's, you know, in something, you know, it's a terrible place to do that. We have some great conservation companies that we can open. Part of the world is not easy. I don't want to see that.
When they
Well, I share my.
walk uphill
Yeah.
like that.
Yeah. I think the other thing that really helps them is that, you know, the soldiers are spread out. That's really essential. It's more conservative life because of the short tolerance. And then you see what how essentially sort of put them into their
Oh.
And they have European biologists, sort of one big framework.
Thanks. Yeah, it's kind so.
Some kind of center.
I can print. Do you like it? No, yeah. It's gonna go out there.
Yeah, it's good. It's really powerful for it. There's like one of them. I can do that. Yeah. It doesn't go fast. I wouldn't.
Yeah, I don't think she needs to do anymore.
Yeah.
It's just simple.
Well, some numbers.
Well, right,
But
but you have some down here.
Sorry, I was thinking.
But that's easy. Anyway, think about it. Because I don't think that other than only the numbers, front and center and being like, you know, we want to use it,
yeah, it doesn't have a, it's such a novel thing. Some things. Some people can really showcase it, but it's also small, but it's fascinating, also efficient.
Right. Yeah.
Yeah.
And then the talks I was going to stare at your ears. Lend your ears. Lend your ears.
Friends,
No more
Romans, and
violent
countries.
Where's it from? Shakespeare or something?
Let me see.
It's in the my undergrad's initial results for English climate phase. I see that for this group,
those going backward or different proportional folds are happening? So they're instead of being like this, they're kind of like that. So you get the resist less of the resistance toward less. It makes sense in my recent data that it was this is
Yes.
No, Adam, you never want to see.
Look at the one or something. It's all easy to say. Is that crazy? No. This is more like it's heavy here. Oh, not nuts. And then somebody was like, what do I do? It's not straight. I was like, that's great. That's
really
great
cool.
news. Write it down.
I have no idea. Doing math there, it's 8 hours a week. I gotta find out what's going on.
Yeah.
There should be some kind of announcement on the whole bunch of football. This setting.
There's a whole bunch of cookies.
This summer knocked down.
This
Offer
series.
of excellent cookies. Incredible.
Who's going first? Yeah, by accident, but I don't do any science on it. It's my I do. It's really powerful for me. So I like it because it's late. I need to bring it inside. I just had
It's like, I know, but not any of those things.
I got it, and it does exactly what I want to do. It's powerful enough to do any sort of like,
Regular-
any sort of regular stuff. I can even program on it. I can't really mix long programs on it, or like from fixing what I can do. I can do like Illustrator. Yeah, and normal stuff like emails and videos. Well,
I'm just gonna announce you went to the SCN room where they have that AC blowing at 66 degrees Fahrenheit. This is incredible.
And now you feel like under the drop.
Yes. Well, there's something I just want to So, I think what we're gonna be happy for me that I do like a nice solo off session, but here's you gotta pay some the AC. So.
Fredo is still running.
What time are we meant to restart?
Oh my God.
Do it.
JJ looks ready. To celebrate. No, look good.
Last figures tomorrow.
It's not the way I work.
You gotta convince him to major in engineering.
I think that's just biology.
Yeah, no, I love that. It's just that. It doesn't. Not to include your original. Yeah. Not the insult or hyperrational. Yeah. No, that's all.
Yes. So I get
I think it's all.
But yes, you can absolutely go look around. Yes. Well, is it time yet? Huh? What they're doing is they're actually taking the time a lot.
They're all,
All right, first draft and a second NSF grant for the class. Same.
Where'd you send it off to?
It just got submitted to the university. They need a certain number of days to play with it. So today is a certain number of day deadline.
We have a shop.
So I'm trying to find out right now because we should bolt after this.
The stuff at a.
Yeah.
At the apartment.
I've seen the apartment. It's amazingly cool. I want a good view.
Yeah, exactly. Also, yeah, I'll just picture them up there redoing the calculations. Going, maybe that creepy voice in the back end.
Yep. There's Twitter.
All right, we're gonna start with first class presentations around police. And Sarah is up first. So I'm going to be speaking today about armor in pictures and how to switch to information. So armor has evolved many times across a lot of different animals. And while it protects them from predation, which is the good, it also comes with costs, which are, it's an incredible amount of mass to live around, and it restricts flexibility and motion. And animals have a bunch of different adaptations to deal with these restrictions. So, like the fighting and the footage of the character can either barely move at all or just stay pretty stable with that cat. Like the armadillo and this very natural cat. They can have armor restricted to one surface of the body and then have the locomotion surface be free of armor so they have that range of motion. And then like this guy in this knight here and the crab, if your entire body is encased in armor, then you're only really able to move at those joints with hips, which are designated for. And this is a completely different ballpark, basically, than living or than swimming in armor. Because when you're swimming, you have to deal with the forces of lift and drag, which are the forces that are perpendicular to flow and run counter to flow, opposing to flow. And I decided to look at Adonis, which is a pretty fish spanning 22 genera and 46 species. And we actually have a number of species that are native to the same islands. And this entire family is physically encased in scales that are modified into this dermal armor process. And these are the three species that I decided to focus on while I was here, mainly because we have sample size of these species. All these fish, as Yanni pointed out, are liquid buoyant and they have some rudder. So their food is probably lift and body mass that they have to live. And as a result, many of them just don't overcome it. They're very effectively overcome. They do have some lift provided by other things, but generally they just kind of hang out on the ground, which is a great study organism for studying free flowing swimming because they don't swim. I find that out far too often. Most of these fish rely on the broken locomotion, so rather than moving their entire body that's encased in this armor, they're using the fins to move forward. And there's quite a bit of morphological variation. So while the two other species here at analysis, including this might look kind of similar, they both have a streamlined body shape. While dragon is here, which occurs in hibernation,
has a giant gradient step, which creates a lot of drag because it's quite wide. And so I wanted to look at how these three different species compare their swimming kinetics and how they're restricted by the body armor and how they deal with these restrictions. So my main questions are these. So do all agonics use the same mechanism of orbital propulsion? We know that most of them use this kind of control thing mapping, but yeah, I just wanted to study it and compare the kinetics. And is the body armor restricting the range of motion in agonics? And in species with a full range of motion, how do they overcome the constraints of this thermal armor and how does that shape the swimming mechanics? So to start off, I took videos of what we do. Okay, so this is agonopsis swimming. Basically, this is a generalized video. You can see that they're mainly using their performance as we expected to for that one. But also it's a little bit of there's a little bit of constant motion as well. And this plot on the right here shows the angle of the tail relative to the head velocity. So it shows the tail's amplitude and frequency along the way. And so they're not using the carbon very much. Likewise, the Protothecus is swimming in similar way. They're using the carbon a little bit more slow motion, but again, they're really reliant on the pictorial species. And then we have our weirdos with the holes in their heads. And these guys are crazy. It's kind of like drunk people walking. On this, all of them are moving, but they're flapping their performance ever. Basically, they're doing everything they can to get themselves to another location. It's really spastic, as you can tell, by the frequency of their flapping and funnel finger. And just to really bring this point up home, I have a plot comparing the kinematics of these three species, and you can really see the contrast between, especially about riding a single species, that you can use species have different local. And again, this is the angle of the tail. So at 0 here is when the fish is in a straight line. Below 0 is when the fish is curved down. And above 0 is when the fish is curved up. So my next logical question, I guess, was, because these guys are swimming so frantically, are they really getting anywhere much faster? What is the purpose of this? The answer is no, they're not. So here's velocity on the y-axis, and there's really no significant difference in velocity. This is average velocity for and there's really no difference in velocity. So despite moving their little tails as quickly as they can, they're not really getting anywhere much faster than other species that are just using people. But the main thing I wanted to look at is the flexibility in body armor. And these two, again, I'm not really using the full body for this locomotion. But this guy clearly is using much more of his color. So I wanted to look at the implications of the flexibility in that body armor and how flexible it is due to and how it influences the kinetics as well. So looking at this coefficient called critical membership, this is the ratio of the curved vertical column versus the straight vertical column. And so you can see that these guys, this is the max that actually curve them. So these guys are freshly dead individuals had quicker bodies much as they could, and that's as far as it goes. So these high coefficients basically mean that they can only reach that C shape, and they're already restricted in how flexible their body is in that whole axis. Whereas while riding is here, basically they can slap their faces with their funnel fins. There is no restriction there. 0.3 basically means these guys can form a perfect O, or as perfect of an O as they could be. So clearly there's some restriction here and nothing here. And my next question was why? Well, I also compared, so this is max curvature possible, and this is the maximum angle of the tail while they're swimming. So it's the max curvature they're capable of, this is the max curvature they're capable of. And basically these guys have a lot of ability to curve, and they use it when they swim. And these guys don't have the ability to curve and don't use it, so they are restricted. Their locomotion is restricted. So, courtesy of Yanni, we have these beautiful
CT scans of individuals that were taken while they were curved. And these are basically to look at internal morphology, like how it's really, how the vertebral column is working with the curvature of the body. So studying not only the number of vertebrae, which tend to correlate with flexibility, with more vertebrae, but also the intervertebral joints in terms of functional rounding issues with them. And how do I a chance to look at the intervertebral joints, especially as I want to that? That's kind of in the future. But vertebral counts, Agonopsis has a vertebral count of basically 34 to 39 vertebrae. And because we're so restricted to bending, I expected to find fewer vertebrae in, or more vertebrae in Bothrioidus because they are able to bend. I kind of gave away the punchline, but they have fewer vertebrae, in fact. So it seems that this bending is not coming from the vertebral column, in fact, but it's some external epidermal armor in origin. And I decided to use SEMs then to compare the morphology of this dermal armor. So here is a picture of the bony plates on the lateral side of the face from all and you can see the plates here. So here's the line between two plates and the spine heading towards the dorsal, or sorry, the caudal side of the face. And as Donnie said in his talk about the Adonis plates, they're not really overlapping that much. There's much more of a joint there. So they're more relying on this bending formation than they overlap, which might be restricting movements. Likewise, when you see the Protothecus, it's a similar morphology. So it's a very flat plate with a joint here and the spine heading towards the caudal portion of the fish. Kind of unsurprising. And then, as you might expect, our rears pop up. And it's a very, very different morphology in the scales. So these look almost more like, I don't know, I guess, ossified bony nodules. I don't really know what to call them. I've never seen this morphology before. And it looks like they're embedded in some sort of epithelial matrix. I'm really not sure what substance this is made of. I have a feeling, just based on the morphology, that this is really contributing to the flexibility of the fish. But it remains to be seen exactly how really anything besides just the SEMs of basic morphology. So in overview, Agonopsis rely on different mechanisms of locomotion due to the constraints of flexibility. So the Agonopsis and Protothecus are really constrained, and they're definitely using it for control as a result. Well, these guys are not really constrained. They're basically using their entire bodies to swim forward. And Bothrioidus dermal armor appears to have very different structural properties than any other aquatic species, which I think is a fascinating look or direction for future projects. And I kind of laid out a couple of future questions that would be interesting to pursue. Like, is the flexibility in Bothrioidus due to a combination of specialization in your joints, or is it simply due to the dermal armor and the properties of that? Also, the increased energy expenditure, because they're doing their tail so much faster, but no change in velocity. What is the benefit of having this extra flexibility? What are they using it for, if not just to wildly flail? And are Bothrioidus sacrificing defense for flexibility? So I think it's interesting to get the country testing in all of the lines and see if they really are as protected from predation as other species, or if they are sacrificing that. And then look at the material properties of the dermal armor. And with that, oh, I have my example for my acknowledgement slide. This is what happens when you try to get them to fish the swim and give up and try to do this by any means necessary. And with that, I'd like to thank especially Yanni for the scans, Mike for his constant advice, Diego for recommending the CT scans that Yanni provided, and the entire class for especially moral and emotional support. Yes.
So they might, it looks like they have similar workouts, but they're different. Do you standardize them?
I did not standardize for length. I basically just counted vertebrae and to see if them were. I'm not as familiar with what people call morphology and morphometrics, so I would love any insights.
Yeah, I think it would be a good idea to take a number of vertebrae that this has and divide that by one to see how many vertebrae there are currently, and that might allow it to be as flexible as it is, although it has.
That's a great idea. It's not a comment, but I was, if you look at the profiling and the it seems like the Bothrioidus has a really different conceptual area and Yeah, I think that'd be interesting. I did a bunch more studies, guys. I didn't get some of that. Mainly, I was just getting differentiation by species because it looks so great different.
It seems like in the Von Gardner, you almost look like a monkey picture, you know, not that it's so,
Yeah, they have much bigger population.
I think that with how many economics there's heads were estimated to be big as the private system, and if they have that much weight, so we have forwards, if they have nothing to do, would it be able to really just
So that's a good idea, but I did look at their massive on these fishes. I didn't present it because I wasn't senior, but because they were all basically in the same location. Along with it. Yeah. Yes, exactly, yes. How is that possible? Albeit it was with string and a bunch of pictures, so I would like to do it more accurately in the future. It was very estimated, but it looks to be in very similar ways. And I also looked at angle of attack of these fish, and it is similar in bronchitis and agnosis, and actually a little bit lower in the Portuguese. Yeah.
So, I wonder what would happen if you like struck reeds.
I'd like to see if that has Aya Cook.
So the Bulgarians don't have those spines in the segment. You have those bent scales. That was actually getting caught up and stopping the so you can start looking at the spines and see if
Yeah.
why have those spines.
That was a thought I had too, but I was also just looking at the plates above each other too, and so I think there is other constraints involved that the spines could be playing a part. Another time,
Alrighty. So I spent my time here looking at the morphological variation of the dorsal spine in triggerfishes and filefishes. And what these are a group of really cute fish that have these enormous spines, which they use for defensive purposes. In this particular scenario, you have a filefish that has moved into a little crevice and propped its dorsal spine up in order to prevent itself from being sucked in by the predator's jaws, as it's not. And you can imagine that if it didn't have that spine there, or if the spine were to fail, or to buckle, or bend, or break in any form, then it would be goodbye to that little fish. So it's a very important thing. And also, not just for hiding in the caves, but in some instances, maybe it doesn't have time to hide in the cave. A grouper approaches it and tries to inhale it whole. And so it can erect its spine and increase its effective body depth. And that is very important for defending yourself against escape-limited predators. So how is the spine, this dorsal spine that's so important to their survival, how does it keep from breaking? How does it cope with these different demands? And so the way I look at these is thinking about them as beams of sorts. And with beams, or any sort of, with beams, you could think about two important factors that determine what happens to a beam and how it behaves under a particular load. Shape, or the cross-section of the beam, is important. Here I have a cylinder and a 2x4 plane in different orientations. And you can imagine if I were to place a load on the cylinder, it would bend the same amount no matter which direction I turned it in, right? Because the cross-section is the same and the load is being applied to that the same. However, with this 2x4 plane, depending on its orientation, right? If I were to orient the plane upright like that, top middle one, and stand on it, it would only bend so much. But if I were to lay it flat, then it would bend more even with the same load. And so the cross-section of the beam is important to how it bends and how it deflects under a given load. But not just the shape, not the cross section, but also the material, what's it made out of. You can imagine that if I were to have a steel plane or a plywood plane, that they would behave differently. With the same load, the steel would bend, plank would barely bend, and the plywood plank would bend a lot more. So this basically summarizes flexural stiffness, which is described as material properties and the shape of the cross section, or the second moment of area. I just keep saying shape because it's a lot shorter. And so I wanted to look at those two properties in filefishes and triggerfishes, which are two families, sister families, that both have spines, but as you can see, clearly have very different morphologies. Filefishes on the left have lots of mini spines protruding laterally from the main spine. With one exception here on the right, which is actually smooth throughout. And then triggerfishes are generally have a more smooth profile with less of those spines protruding. Now, how is this affecting the shape of this beam, this spine? So to have a meaningful way of thinking about this, we took the spine and said, well, how does the spine behave differently with all those mini spines from a simple cylinder of a similar size? Because we're comparing fishes of different sizes with different spine shapes, the best way to standardize for their differences in size and shape is to say, well, we're going to compare them all to some idealized cylinder of the same size and roughly the same shape, minus the little mini spines and protrusions. Now, with this comes this idea of eccentricity, which is the longest part of this cross section divided by the shortest part. And so in this circle, which has low eccentricity, but as you stretch one side out, it gets a different eccentricity. And it goes from being this cylinder, which it doesn't matter where you apply the load on in the cross section, it's going to behave the same, to getting more of like a plank, where if you stand on it on one side, it's going to deflect more than if you would stand on it when it was like upright, something like that. Now, the reason this is important is because we're dealing with complicated shapes, and so we can't just sort of, oh, it's like a cylinder, so clearly it's going to behave no matter how, from where you apply the load. You have all these spines, and they're not just symmetrically placed, so they're staggered throughout. You go left, right, left, right, as you go up along the spine. So how is this causing the shape and the material, or the shape, the cross-section of the spine to change? So, it's a lot of information, but it's good stuff. So on the x-axis, you have the length of the spine in percentage. So you have 0 to 100% from the base to the tip. And then you have on the y-axis the eccentricity. That's what I was talking about, going from a cylindrical shape to a more plank-like shape. And each line is a different species. And what I want you to glean from this figure is that the white dashed line means that it's cylindrically shaped throughout. But that's hardly ever the case with people. And it's unsurprising because they have all these spines. This is exactly what you'd expect. But what's interesting about this is that they are somehow, along the way of the spine, managing to change the way they behave as a shape without changing the whole shape of the spine. So in other words, by interspersing the spine with little spines on the side, they are, in certain regions, increasing the second moment of area, that is the resistance to bending it has. And because that is a complicated figure and it's not as meaningful, this is a mean of those lines. So each bar is a different species. And you have on the x-axis of the species, and on the y-axis you have eccentricity, right, whether it's cylindrical or more ellipsoidal. And if it's at 1, the way I measured it, that means it's sort of shaped overall like a cylinder or some regularly shaped cube. And the farther it gets away from 1, the more different it is. It behaves differently in general. the cross section overall would have a different flexural stiffness. Now, as far as general trends go or anything like that, there don't seem to be any obvious differences separating the spines of these two families. Both seem to employ different strategies and shape. Some of them have low eccentricities, like in trigger fishes right here, and some up there, and some of them have high eccentricities. And I think the main thing to take from this is that the higher the eccentricity here, it means that in one direction the spine is resisting bending more, and on the other direction, so if I were to have the spine here, let's do this. Yes. I am the front of the fish and I have my spine here. That means that the higher number, I'm resisting bending more like this, but it might be easier for me to bend like this. And if you remember from that cave drawing, it's more important to resist bending in this direction than it is in this direction because you're getting pulled in this direction. And so you need to have a strong spine for that. Now, as far as spine mineralization, like how ossified are these spines? Again, there aren't any trends associated with the families or the general shapes of the spines, which is interesting because it makes me wonder about what the correlation between spine mineralization and eccentricity is. So really what I want you to take from this is that the ossification levels are roughly the same for all of these. There are two exceptions, which are the two towards the left that are pretty high, and I think that has to do with the particular scan and the way we measured it. I think we might have to recalibrate to get a better measurement of ossification. Because the other ones were from different scans and they got more consistent readings, and those might be funky. So what I expect to see is essentially that they're more or less the same. And what that implies is here is ossification on the y-axis and eccentricity, the shape on the x-axis, and here are all the species. Is that, and there are those 2 points essentially that were highly ossified that I might have to remeasure, is that you have most of your variation in shape and not so much in the ossification. So what's really dictating the flexural stiffness of the spines isn't so much the ossification, the material properties, but the shape. So with that, thank you all very much to all the people who helped me one-on-one, in general, Beth for her support and bringing me out here for sure, Adam for advising me on how to take these measurements, and maybe I did it poorly and we'll have to talk some more, so I don't know, but we'll talk about it in more detail. And yeah, thanks. Questions? Noah. Yeah, I think it's pretty much the same. So if I go back to this figure, the triggerfishes have a second dorsal spine behind the main spine, so it looks different superficially, but at the base, the locking mechanism is the same. So you have a single spine here, a single spine there, but then you have this tiny little one. The locking mechanism is under that second dorsal spine, and it's also here too. It just doesn't have that large spine. No, but I'd like to check that out.
I had a question about the implications of the mini spline. So as I understood it, you were saying they alternate to go long and then increase the second momentarily in different directions.
Yeah, and it eventually evens out because they're alternating.
It just seems that the strain of stress would be distributed across the whole spine in a lot of cases, and the whole large spine. So that if you're having perfect second moment area for that particular stress, you have another place where it's just weak and the break is just going to occur there. So I'm wondering what the net benefit is thinking about the spine as a whole rather than just the local.
Yeah, I'm not not sure. That's really interesting, and I'd really love to think about that some more because I've wondered the same thing. I also thought about these spines as sort of gripping mechanisms. So imagine being in that little crevice. These spines might help you actually grab onto the rock or whatever you're in. And so it also gives you an added benefit to having the spine. Not only are you sort of preventing getting pulled out by having a spine, but these little barbs are also hooking onto that crevice and keeping sort of. Okay, Ed?
Some other structural components of the body, as well as for this one.
I looked at them, but I didn't do any analysis of them. So I'm interested in it.
I was just for instance, get breakers for differences in the spine between populations.
Differences in breakage, I don't know. And
If that's even that.
breakage, whether like that's been reported or like rates of breakage on species and like,
Yeah, I mean, how much damage do they actually get to that spine in terms of daily lives?
yeah, I don't know. I don't know if there's any data on that. I didn't find any, but there might be.
I can tell you just if you get out of together and tell them, having that, I was watching some people go by and I thought it was gone and it's not. No, it's a concept trigger, but the head ends sticking out. So,
Oh, man. Did he say anything about the spine? Like,
the spine was inside.
oh, well, yeah. See, that's yeah. That day for that trigger.
It was increased shallow, so it was probably smaller.
Hmm.
And the larger.
All right. Well, thank you.
All right, hi everyone. Today I'm going to be talking about the function of the spiral intestine in chondrichthyes. So, I think we can all agree that sharks are largely carnivorous. They consume very high protein, high fat diets. And this consists of things like maybe other smaller sharks, marine mammals, bony fishes, even large amounts of zooplankton. And since sharks are consuming prey all along the trophic cascade, they are a big component in controlling the biodiversity of the fishes that we count as a food source and economic resource. So learning more about their nutritional physiology is actually really important. All right, so they're highly carnivorous. They consume very high protein, high fat diets. So presumably they would have a digestive tract that is prepared to take all that protein and lipid and convert it into usable energy. So one way they do that from a biochemical standpoint is by having high levels of protein and lipid degrading enzymes in their digestive tract. And another thing about sharks and understanding all their feeding habits is that they are known as yield maximizers. So they generally have very large meals on kind of an infrequent basis. So they need to be able to slow the transit rate of food going through their gut in order to conserve the nutrients in time before they get their next meal. So one way that they've been presumed to do this is by having a spiral intestine. You may have heard referred to as a spiral valve. It's a series of intestinal folds in the mid to distal region of the gut, which is, as I said, presumed to slow the rate of transit through the gut and increase the absorptive surface area, although there's really not a lot of quantitative evidence of this. So to give you an idea of how little we actually know about spiral intestines, this illustration was originally published in 1985 and is still cited over and over and over again and has been for over 130 years, even as recently as 2011 in a really popularly cited review of
So it's time to kind of step up the game a little bit, I think, and find a new way of looking at some really different structures. But we do know some things about them. We know that all known sharks, snakes, and rays have these endodermal systems along with some fish, such as the fish. We know that the number of intestinal folds can vary between the species, and we know that they come in its four main structures. So they have the column shape, funnels pointed towards the posterior end, funnels pointed towards the anterior end, and then this new scroll shape. Right, so my main goal was to first figure out more about the morphologies of the different spirals. So as I said, we do know some things about them, but most of what we know is based off of dissections and illustrations. So the structure of the spiral intestine when you go to do a dissection is obviously kind of broken to do that. So you're not really getting a full picture of what's going on. My second goal was to measure the flow rate. As I said, it's really slow transit through the gut. So I had a really high time doing this, which I'll talk to you about later. And then my final goal while I was here was to determine how the spiral intestine smooth muscle contractions actually move digestion through the gut. So we'll start out by focusing on this first question. How do spiral morphologies differ between the different species? So my main goal here was to kind of recreate that iconic 1885 image, but using a more modern technique. So I looked at CT scans, I freeze-dried the intestine samples, I put CT scans and created 3D images of them. So we have this one, this is in the spiral shape from the stomach dogfish. The blunt-nosed stingray has the funnels pointed towards the posterior end. The crown-nosed ray has the funnels pointed anteriorly. And the bonnet-head shark has the small intestine. So this is what these intestines actually look like in their first non-photographic, non-illustration form. What's really cool about these 3D images is now we're not constricted to looking at it just in a one or two-dimensional plane, but you can move the spiral around and get an idea of how things might be flowing through the intestine. We could use these images to quantify things like volume of the intestine, the actual surface area that the different tissue folds are producing. So this could be a really beneficial quantitative tool for the Oh, and one other thing I want to say about this, actually, is I talked about being able to visualize flow. So you can kind of see this is the spinal intestine from the spinal dogfish, but it looks like there's a central lumen, which has never really been discussed. It's always just been assumed that food goes into the spiral intestine and spirals through all the different folds. But the evidence of the central lumen means that some food can pass directly through. And that's something that we haven't really been able to discuss before. There we go. Okay, so now we're going to move on to the second question. How is flow rate affected by the presence of the spiral intestine? So I took a carboy filled with a known amount of water and attached a clear, just regular plastic tube onto the end of it of a known length and diameter, and measured the amount of time that it took for a liter of water to flow through that tube. And then I used that as a control to compare and do the same thing for the proximal intestine and the spiral intestine of 4 different shark species. So I looked at the bottom of the spiny dogfish, the bonnet, the bonnethead, and the scallop. And then the proximal intestine are the bars with the little dots, and the spiral are the stripes. And you can see that flow rate is much slower in the spiral intestines as compared to in fact, it's about 3.5 times slower through the spiral intestine. When we compare this to the resistance of the different intestinal types, we see that it's in inverse relationship. So as the resistance is increased, because it'll be due to all those intestinal folds in the spinal intestine, the flow rate. So I thought this was really interesting.
saying for a really long time that I haven't really talked about before. But what I wanted to test next was whether flow moves the same way in both directions of the back. So this is flow the normal direction from the anterior end to the posterior end, but would it look the same if you were kind of back flow the opposite direction? And the answer is kind of no. When you look at now the flow from the posterior end to the anterior end, it is indeed slower than floating. So flow is moving even slower if it's back floating through that direction. And also the resistance is higher in that direction. And the reason why I thought that this was interesting was this evidence that backflow isn't as effective, and the evidence from the CT scan kind of reminded us of a Tesla valve. For those of you who don't know what a Tesla valve is, it was patented by Tesla in 1916. It's a type of valve that uses one-way flow without the use of any mechanical parts or energy. And it's actually never been observed in a natural system before, so it hasn't been put to a lot of use for that reason. But could the Stark spiral intestine kind of be the first natural evidence of that? There's something here that spiral is being on the back, very similar to intestine valve. So an example of this in nature is kind of interesting because we have seen one before, so maybe there's more applications that we can say about the intestine valve. Okay, so for my last question, I wanted to look at the muscle contractions of the spiral intestine to see how it moved digestive material through it. So I used a science doctorate for these experiments, recently guys, and tested the digestive fluid. I left the digestive tract in the animal and injected a known amount of food-dyed corn syrup into the anterior end, and then injected the walls of the intestine with acetylcholine, which is a neurotransmitter that stimulates smooth muscle. When I do that, I'll show you a little video. This is sped up to 2 times its natural. Very cool. So I took a lot of pictures of this, and what I did was I counted the number of contractions that occurred in a minute, as well as the overall time that it took for the dye to pass completely through the spiral intestine, which is 50 successfully every time. And from that information, I was able to calculate the average number of contractions that it took for the digestive, the corn syrup, to move completely through. And it was pretty standard throughout, actually. Even though the time varied, the average number of contractions that it took to move all the way through was about 244 or 52. So pretty average range. All right. So, 3D renderings, in summary, are kind of the new frontier, I think, in examining digestion as far as the spiral intestine is concerned. We can really quantify some of the morphological questions that we've been asking. We can also use them to visualize flow. Sure enough, the spiral intestine does have a slower flow rate than the proximal intestine, about 3.5 times slower. And we can now quantify the number of muscle contractions that it takes for food to move through the system. So this kind of information paired with gastric evacuation rate, which is used in digestive physiology studies often, kind of helps us paint a picture of how the spiral intestine plays a role in the whole digestive system as a whole. And with that, I would like to thank everyone, Adam and Alex, for all of their support and help on the Doctor program, for coming to be able to attend and develop the same research. Cassandra, you've been amazing, and Fish Class Cohort, thank you all very much.
That union actually connect inside the other. That one that's inside the other.
This one? What do you mean? Does it actually connect to the side of the
I just
So,
don't
like,
think
if
it
it's
needs
not-
to just go through the.
Well, it does connect directly to the proximal intestine. Yeah, maybe. Do you think those are different, or is one different? I think it's only a good place to start. It'd be interesting to see, especially since the different sharks are looking at different diets, if they handle the different diets differently. Yeah, that would be.
I know there's some combined with the grass and I've also seen that they eat a lot of crabs. So, is imaginary connection between the spiral down organization there and the existing diet?
So that's kind of where I think essentially play, and it's kind of hard to tell with the other spiral intestinal villages, but usually when I did a lot of examining shark food with this project, if they are eating crabs, a lot of the kind of shell material just comes through. And I can't imagine that grinding through all these really big spirals, so something like that might be really concentrated. Yes.
So when I saw the current pulse is going down, it's all went in one direction, right, more or less, the way the stuff out.
Right.
I'm just wondering, do you reverse current pulses, or is there some role for just ensuring the sleep rather than just transporting around the sleep?
Most of it was kind of unidirectional. Actually, interestingly, when I did the same thing with the proximal intestine, and the proximal intestine I couldn't get to contract at all. And when, at the end of the experiment, when I removed the whole digestive tract from the animal, the green dye that I had injected into the proximal intestine kind of evaporated out to the esophagus. But that wasn't the case in the proximal, or in the spiral intestine. Thank you.
All right, so today I'm going to talk to you about food fish that I've been working on, specifically New World food fish, and I'm going to be looking at kind of some of the morphological consequences of miniaturization and how it affects morphological evolution in this region. So when we think of body size might be the most kind of obvious phenotypic character right away when you look at an organism. You know, great example is whales, right? Sea whale, you know, big right away. And there's a lot of selection for body size. And you know, in a few different ways. So it could be, throughout ontogeny, right? Having to do with limiting possible predators that feed on you, or what you could eat. Even for sexual selection, there's selection for body size. And even for niche segregation, like these little obligate gastropod dwelling fish. And kind of one phenomenon with body size that we see in a wide variety of metazoa is miniaturization. This is just a rapid change in body size from an ancestor. So kind of the questions with miniaturization are, how exactly does the body change? Right? So in some cases you have smaller bodies that develop either through truncation of development. Sometimes there's full scaling of elements, and they're just mini copies. But miniaturization also sometimes creates morphological novelty. So in fish, this is one of my favorite examples. This is a priapum fish. They're a aphroditomorph that has a intermittent organ, basically like under their throat. And they're really small for aphroditomorphs, but full lineage kind of has developed this. So when we're talking about miniature fish throughout this talk, I'm going to follow the definition of Weitzman and Berry, who basically make the cutoff at 26 millimeters standard length. So they're equal to that or smaller. So another thing that is related to body size is kind of Cope's rule. And Cope's rule is basically body size evolution over time. You see an increase in body. And if we wanted to make a imaginary example of this, we could use possibly the San Juan Island's most elusive and endemic creature, Chris Pratt. Let's say we had a lineage of Chris Pratt we wanted to identify over time, or observe over time. You might see through evolutionary time, there's an increase in body size. So why are clingfish great to study this, especially Gobiosaki clingfish? So these are just a subfamily within the clingfish, mostly limited to the New World, and it's because they vary a lot in body size. So this is a adorable #Fukigen little acertops clingfish, but we also have these big nasty brutes like this. This is Sicaces, which is #ugly. I don't know, but there's a lot of variation in these body sizes. So, kind of the two questions I'm interested in asking here are: do Gobiosaki fishes follow Cope's rule? So, do we see a general trend of enlarged body size over time within this clade? And the other question is, how does miniaturization, kind of produce different morphological combinations within species that have undergone? So, are they simply just tinier versions of a really kind of generalist Gobiosaki, which in this case would be Gobiosaki, is about as generalist as you can get in this subclade. So the ones that catch up here, Gobiosaki anthopus is in the subclade, really general phenotype for the group. And just to look at body size across the tree, basically warm colors are going to correspond to smaller body sizes, cooler colors, larger body sizes, and Sicaces, that big nasty clingfish. His sister, basically, the rest of the Gobiosaki clingfishes here. It's one of the bigger ones out there as well. We also get big increases in size and some of the other Gobiosaks. And one thing to note is kind of the phylogenetics of this group are really not great. This is a phylogeny that Kevin Conway's developing right now. It's very much in flux. So hopefully we'll have some more data to add to this. But kind of it's problematic here. You can see that they're not exactly monophyletic as is right now. So from that figure, you might be able to kind of predict what's going to happen. But when testing Cope's rule, but to test Cope's rule, basically what I did is I performed a phylogenetic generalized least squared regression. Maximum standard length is a function of kind of the phylogenetic age, which is calculated at the nodes and then applied to the subtended bits. So we had 20 species for this. And we can basically see that there's really not a trend at all. So our slope is not significantly different from 0 at all. It's 0.19. And really Gobiosakines don't really seem to be following Cope's rule. So the second question is understanding morphological diversity. Are these miniatures just shrunk down versions of the generalist, or do they have interesting combinations? To do this, Kevin scanned 15 species of Gobiosakines here with the sky scan. I worked on them and reconstructed surface renderings and 3D slicer. I then used a landmark editor, which is through UC Davis, I believe their anthropology department, to place 12 landmarks, so both on the left and the right side of it. And then we analyzed it in Geomorph, which is an R package. So Geomorph has a bunch of really useful utilities if you're doing morphometrics, some things such as allows you to do generalized Questies analysis, so to do superimposition. And then it also has a bunch of useful tools to actually do some hypothesis testing. And what we used here is we basically performed a morphological disparity. And this is our morphospace of Gobiosaki clingfishes. So in blue are species that are miniature. I put Gobius, which is the generalist in this case, they're black, and just other Gobius species are going to be gray. And this is just some dorsal view of the fish right now, lateral longitude. But the first, I'm only going to show 2 axes today, but I'll tell you a little bit about the third as well. There were only 3 that accounted for more than 10% of the morphological diversity. But the main axis we pulled out was that accounted for 28.3% of the diversity was lower jawline. So kind of from your right to the left, we have longer jaw Gobius, moving down here to Runicola, which is a kelp fish, and Sikiaces, that big ugly guy that I showed you guys earlier, that have much shorter jaws. And PC2, which accounted for 17.7% of the variation, wound up being basically how broad the head was, so the head width. So again, Runicola, kelp fish, kind of the extreme here, Sikiaces, at the other extreme with really broad head, and kind of everything else is sort of intermediate. So one of the things that we see is these miniature plainfish exceed a little bit from these generalist plainfish phenotypes, but really not that much. Before I move on, PC3 was very heavily influenced by a lot of the eye characteristics, and it's basically how much of your head the orbit takes up and the surface of your head. And we performed a morphospace disparity analysis on this. So basically, it's looking at Euclidean space and measuring distances. And basically, we found that Gobius had the least amount of disparity among them, followed by the miniature Gobius, and then all the other species had the most. And kind of the only significant kind of difference between these groups was the other Gobius species were significantly different from Gobius, kind of the generalists themselves. The miniatures were not significantly different from either the Gobius generalist or the other species in this analysis. So the main conclusions here are Gobius and plainfish body sizes don't follow Coates' rule. I think in general, fish have a tendency to break away from that. I can think of a bunch of examples, specifically things like killifishes that you definitely have a decrease in body size over time, as well as some of the cichlids tend to do that. So I think fishes are a really interesting system to kind of look at Coates' rule because they tend to break away from it. And the other conclusion is that these miniature species of Gobius and plainfishes do not really have a lot of morphological disparity compared to just these generalists. They really do seem to be pretty close to just these shrunk down versions of generalist Gobius. They occupy fairly similar areas of morphospace, and kind of the two kind of weirdos in this analysis were Sikiaces and Runicola. So some future directions that I think would be really interesting to do, go with this kind of project are, do we find similar patterns in other Gobius subfamilies? So just from looking at some of the scans that Kevin has done for other Gobius Gobiusacidae, there tends to be a lot of kind of really weird elongation that Gobiusacians themselves don't have, but other subfamilies do. So I think I would expect kind of to find some more kind of disparity among those folks compared to Gobiusacians. Kind of the limitation of this is there's really no good phylogenetic kind of comparative framework for Gobiusacids at all. So this is really one of the first molecular phylogenies available. And the other thing is, basically the shape is the same, but I didn't really measure ossification. These didn't really have any phantoms with them to kind of do that. But I think it'd be really interesting to look at, do we have areas of these miniature plainfish that are just not really getting ossified? Maybe they're holding fairly similar shapes, it's not undergoing ossification. The last thing that I think would be really interesting to do is look at these pectoral pelvic girdles. So, a lot of people are familiar with plainfish and their ability to stick to surfaces, but these are really important for both feeding, so they'll actually hunker down to do some suction, and also just attaching the substrate. And goby stockades are found in freshwater rivers all the way to coral reefs and the deep sea. So with that, I'd like to thank Cassandra, Alice, Yanni, and Thaddeus for helping me troubleshoot some issues with 3D Slicer and the landmark editor, and Dexter for helping me section some fish out. With that, I'll take questions. Yeah. So a lot of the stuff I've seen has been, I mean, it basically comes down to ecological differences. So whether you're following it or breaking away from it. So I think usually breaking away from it, it's usually seems to be entrance into new habitats. So for the cichlids that I work on, a good example of this is the shell-belonging cichlids. They radiated really recently, and that's because they have really tiny body sizes that evolved recently to kind of live in this. Kind of the opposite example of that, following Coates' rule would be like horses, right? So horses start off as really tiny creatures that basically were browsing and not really grazing actively, and then over time, they turned into grazing. So I think it's really ecology that's kind of driving, following this rule. Yeah.
I think then that the evolution would relate to evolution of habitat.
Yeah, so some of the issues with this group is, in terms of dating it, it would be difficult because there's not really a good fossil record for it, which is one of the troubles doing this study. We have to basically use a molecular clock. So we don't have really good estimates of diversification times for them. But I mean, it would be pretty easy to look at ecological invasions if you could date it pretty easily. You could if you have accurate divergence. So if you could accurately figure out kind of when they diversified and put like an actual time and millions of years on it, it would be totally doable because then you can go back to geological record and kind of see formations of certain structures. So most of these miniatures are on coral reefs. Yeah.
Okay, so good afternoon, everyone. Thanks for those who are spending with us. And in the last one, I hope that you do a great job of the That's it. So I'll start talking about cold fishes that are the topic of my PhD project. And in here, I have been investigating a specific skeletal component that is usually found in cold fishes. But I was starting to talk, giving a brief introduction. Who are cold fishes? They are taxonomically considered a whole order but before the forms. They have the original distinction by this large head and wide pectoral fins. And they are also known for having these really complex vocalizations. They have things like the sonic muscles that allow them to vocalize from mass defense and from making this. Presently, we have 82 species allocated in 25 genera, and these species they are worldwide distributed. And around the world, they inhabit mostly coastal and brackish waters. Locally, in the San Juan Islands, we have Coryptes and potatoes that commonly known as midshipmen. And this genus, not only potatoes, but the whole genus, they are known for having these photospores that can be made by bioluminescence. So now going to the complex itself that I have been looking for. So Tate Reagan in 1912, they named it as the dorsal spines of toadfish. They characterized the order by having
dorsal spines is like supported by what we call it a fixed basalia. And when I started looking at that, and he didn't give any other like description, do not indicate exactly what that means. So for a long time, everyone had been saying that to support dorsal spines, such as dorsal fin rays, are pterygium spores. So what means with this fixed basalia? Then into the darkness now of the skeleton and checking what could it be. So I have the dorsal spine region that means that, and one real. So Wiley Johnson in 2010, they rearranged it and related this definition as calling this basalia or dorsal spine 34 configuration as a crowded configuration. And looking to this slide, I can see easily understand why we call this crowded, because there's a lot of stuff going on here. But I could highlight exactly some regions of interest and what could be considered this, what we call crowded configuration of probably what could be the basalia. So we have here the dorsal spine and the force highly nested within the neural arches. They are highly articulated in that. And not only that, you have these epineurals, fully and highly developed, highly ossified, and the anterior epineural medially articulates the neural arch, and posterior laterally articulates the clavicle. Pretty much doing what the bundle ligament or the ossified bundle ligament does in capsule. So looking at that, looking at all these arrangements, I started wondering, does this complex occur in all butterfly species? Is that indeed a unique feature for butterfly form? And if it is, does this arrangement vary among different species of butterfly form? And if it varies, does this variation, does this bones, the variation of finding these bones, does it vary in phylogenetic information? And it's quite interesting because I just wanted to go to my project because the interrelationships among the subfamilies and subspecies are totally not resolved. This is data from Greenway from Greenfield collaborators, and they cannot resolve how those subfamilies are related to each other. So to assess this question, I CAT scanned several species from different museums, and we did a post-scan label that was segmenting the image from our software. That's pretty much each scan generates around 2,500 frames, and then we went through every frame and select which we could interest to expose the stuff and the region we want. So for this study, we examined 14 species from 11 genera, and these 11 genera, they are representing at least one species for each of the subfamily. We have access on 4 subfamilies, one was beautiful. So starting with those now, that we indeed found that the basalia complex, it means the epineurals, the large and fully developed epineurals articulating with the first vertebral neural arch. And dorsal 34, the dorsal spine complex, highly nested within the neural arches. We found this arrangement with some sort of variation. We found that spread through all the species that we investigated. So we kind of assuming that this could be the characteristic of this disorder. And to make sure that we're not just like making a flaw definition, and we start comparing with some outgroups, comparing to other groups of species that could just like highlight some sort of this characteristics could occur in other taxa. So when I checked mostly in gadgets, but I also checked in literature. So in gadgets, we don't have any of these. They get narrows are frequent developed. They barely contact the neural arches. The dorsal group force, they also do not contact the neural spines. So to the negative, that's indeed a characteristic of this group. And if you look at the other side of the tree, the higher trichomorph. So looking at trichomorphs, now I use it as a proxy for a more generalized trichomorph shape. although they have ephemerals that came from Agnew neural arch, they are weakly developed, not even getting close to the development of the ephemeral in cold fishes, and they also do not contact with the placement. And likewise, the big receptor force are just barely just contacting their teeth, but they're nested as a fine cold fishes. The third force highly tight connection with the neural arches. So we could establish, now we can hypothesize and say, okay, using these found in toad fishes, this is unique in toad fishes, but we need this arrangement, we need what we call as causalia, all this complex or crowded configuration. Does that vary among the different species of toad fishes? And I'm looking now at just the ephemeral series, this one that has coloring red. So in a subfamily of Bacteroidean and Corectini, we have a single ephemeral, highly ossified, which articulates to the first vertebrae and the placenta. All of the ephemerals are just laying over the myosecta. They are not contacting the vertebrae. However, when we look at Halospine, subfamily and Halospine, all species that investigated have not only the first ephemeral, but also the second ephemeral contacting the first and the second vertebrae. In an oblique view, we can see easily that they are both of these bones are really elongated and they need the giving additional support for the articulation of the patellar. And these are subfamily Halospine. This is really interesting because not only the first ephemeral is higher on spine, but also the second and the third ephemeral are projecting over the first vertebrae. They don't have this one-to-one relationship as solid Halospine, but actually the continual ones are kind of moving forward and articulating in the first neural arch. And what's interesting, not only the first neural arch, not only the neurals are moving forward, but all neural arches and spines are kind of bending and moving forward continually in fish. You can see in the oblique view that the first neural arch and spine, they're kind of projected anteriorly, they bend anteriorly. So it's really interesting. And another characteristic that would be helpful to distinguish the families in morphology that we heard before. These are examples of that different species of each subfamily. But what's more remarkable that in Corectini, they lack the crash within the core. All of the ones have that. And the last character that I investigated is how the herbivore articulates with the neurospines. So we established, okay, they are really highly nested among different neurospines. However, in Corectini and Halospine have this one-to-one relationship, one herbivore articulating and sitting over a neurospine. In contrast, that other Bacteroidean and Halospine, we have within the third and the fourth neurospine, we have two herbivores. That's quite interesting because we look at outgroups to check if there's indeed a unique variation within both fishes. And usually what we find this one-to-one relationship among neurospines and herbivores. So assuming that, we can probably hypothesize that this is an apomorphic condition and this can be a synaptomorphic for the group of these families, try to help these relationships. So now going to my partial conclusions. So yes, the morphology of the ephemeral and herbivore is unique about the forms. They are really cool. And they are found formally in different taxonomic levels. You have characters that might have the help to define families, and you have characters that might have group families. And this duplication, I'm assuming a duplication. We need to make further tests and further tests to say the duplicate. But this kind of second duplication, the second herbivore can be a bit kind of anamorphic for Bacteroidean and Halospine. And this is a functional morphology course, and I have to wonder about the function of this complex. And a really interesting thing that came out when I was watching Ian's videos, this might be highly related to how they move the head, how they bury, how they live in this complex. Because toadfish that we have in our aquarium things, they're really strong. They can carry huge rocks. They're really strong. They can move large heads. So this might be related to behavior. So like analogy, I'll propose adding that it was open CAT scan to do whatever, to scan whatever as much as we can, great. And then Alice, her private classes, I really enjoy it. Cassandra, that's it. Cassandra is like wizard of coding stuff. We had a lot of fun. And off this fascinating, you guys are great, so it was a great time. So that's a few questions.
I have a purely hypothetical question. If your PhD advisor was watching this live stream with both of his daughters in his lap, would you have anything to say to those two girls?
They're cool. I like that. Hi, Claire. Hi, sweetheart. My wife's son is also watching that.
Okay.
Sometimes when they're fiddling around with bones at the back of the skull, it's associated with sound stuff, and you kind of pop in your mind for these guys.
Yeah, I mean, yeah, I mean, I have been wondering about that, but Eric and I, we have been studying the swing bladder and how the morphology itself. But what usually the swing bladder, I don't have a mental picture, but the swing bladder kind of projects, your earlobe kind of projects right underneath the ventral bone along the carotid and above the occipital. So I think that this might be just like helping to transmit the sound, because the lobes are kind of contact directly the floor of the body cavity that's right underneath the skull. So I don't think that way, but I think there's like hypothesis. Maybe I would say so. Maybe just like we had it in a spider findings that we had there. So I wonder about that. Nice. I promise I'll finish the paper, Eric.
Thanks everyone for playing. Shut it down now.